The Royal Swedish Academy of Sciences has today decided to award the 2020 Nobel Prize in Physics with one half to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity.
Yeah, good morning. Good morning, Roger. Good morning, everybody, wherever you are. Welcome to day 4 of the specially online event honoring Roger Penrose on the occasions of his 90th birthday and Nobel Prize. And today is on pre-Big Bang universe. Roger's ideas on conformal cyclic cosmology. And we have 4 excellent speakers in this area. And Roger himself will be the chair. So Roger, please take it away. Good morning.
Okay, well, good morning. I'm very pleased to introduce our first speaker, who's Paul Todd. And it's very appropriate that I introduce him first. For a long time, I had been worrying about the fact that quantum gravity, whatever that might be, seems to predict a completely different answer for the future singularities from what we see in the past, which is the Big Bang. And the Big Bang seems to be characterized by the Vahe curvature, the conformal curvature, that is being 0, or at least very small. And I tried playing with that idea for a lot and not really coming up with very much. But then Paul had this idea of using a conformal stretching of the Big Bang. And instead of saying directly that the Vahe curvature is 0, you just say that this conformally stretched Big Bang can be continued into something prior to the Big Bang. Now, this something wasn't supposed to be anything real. It was a fictional space, but it produces a very strong condition on the Big Bang. It doesn't make the Vahe curvature 0, it makes it finite. And so it was a huge step. And also the equations that he'd worked out concerned with this crossover from the pre-Big Bang fictional entity to us was very important in my own understanding of how to treat these things. So let's Paul come on, take over from here. I'm very happy to hear what he's going to say about it all. So Paul.
Thank you, Roger. So I'm going to share screen. and remove the thumbnails. So this is, I'm going to talk about the mathematics behind Roger's conformal cyclic cosmology. The later talks will be concerned with the observational significance of it. It stands or falls with how well it accounts for observation, but there's whether it does stand or does fall, it's very elegant mathematically, and I want to try and give a sense of that. This is the abstract I have on the website. I'm seeking to make this accessible to non-specialists, so that would mean people who haven't done mathematics since high school. So it'll be diagrams and not formulas. If you want the formulas, you can find them. They're readily available. They're easy to find. But if you can get a sense of it through the diagrams, then that's, as it were, my aim. Okay, doesn't want to advance. Right. It's also going to be a homage to the overhead projector, which is something that I've grown up with and which is now vanishing. But I love these colored pens, basically. So this is going to be the mathematics behind Penrose's CCC, which is Conformal Cyclic Cosmology, which is such a mouthful that you want to call it something else. And I'm going to give you 5 thumbnail sketches of different bits of mathematics, bits of physics, which lead to the CCC down there at the bottom, the fifth point. The first is going to be a talk about curvature. I'm not going to define it. I think we've all got a sense of what it is, but I want to show some ways in which you know it's around, you know you've got some. Then special relativity, which is, if you like, the geometry of the world, but without any gravity in it. Once you've got that, you can then put the gravity in, and then you've got general relativity, which is the world with gravity. Once you've got general relativity, there are 2 kinds of things you can do with it. You can look at the solar system, the orbits of the planets, and discover that Newtonian gravity doesn't do the perfect job of describing how they move, but general relativity is a significant improvement, and therefore, if you like, is correct. But you can also go large with general relativity, move out from the solar system, move out to galaxies, move out to clusters of galaxies, and move towards making mathematical models of the universe thought of as a single object, and that's cosmology. And once you've got the knack of that, then you're ready for Roger's outrageous suggestion, which is what he called his conformal cyclic cosmology. So the first bullet point is going to be curvature, and the canonical way of talking about this is you think of the ant on the surface of the orange. So here's the ant. Most ants are female, so I'm going to call her she. So she's moving around on the orange. She can move in any direction on the orange, but she has no notion about the third direction off the orange. Nonetheless, she wishes to study geometry. And of course, she has a problem because on the orange, there are no straight lines. And the first thing we do when we do geometry is we draw straight lines. And so the idea that she has is to say, well, let's drop the notion of straight lines and replace it by the notion of shortest curves. So if we've got 2 points on the orange, then of all the different curves through those 2 points, there will be one which minimizes the distance. And that's what we'll use instead of straight lines. 2 points, there's a blue line, a blue curve, which is the shortest curve. And then all the things that you're normally familiar with about 2 points determine a line and so on and so forth, that will continue to work with shortest curves. So you've got that idea, now you start to do geometry. And so the ant looks at triangles. I've said tiny, I really only mean small, because you don't want, as it were, the 2 points to be round opposite sides of the orange, or complications can ensue. Now, if she makes her triangles on the orange, then they're going to look like this. They'll be made with bits of curve like that. If by good fortune she found herself on a whiteboard, then her shortest curves would actually be straight lines, and she'd be doing the geometry that we already know about. And there's another possibility, which is not quite so obvious, that the shortest curves might end up looking like that. And if you want an example like that, it's down here at the bottom. If you think of a saddle, so in one direction it curves up and in one direction it curves down, then this is the kind of thing that you get on a saddle. Okay, so along comes the ant. She draws a triangle. She measures the angles. If she's doing it on the whiteboard, we know she's going to get 180 degrees. If she's doing it on the orange, well, you can see the angles are going to be correspondingly larger than they were over here. And so when she adds up the angles, she'll get more than 180. And if she does it on the saddle shape, when she adds up the angles, she'll get less than 180. So the idea here is, you know, in this kind of geometry that you're in the presence of curvature if, when you add up the angles, they're more than 180, you say that's positive curvature. You add up the angles, they're less than 180, you say that's negative curvature. If they're equal to 180, you say it's zero curvature, but for conventionally, you always say flat. It's flat. Okay, it's flat. Now you can also do this by looking at the areas. If she looks at the area on the whiteboard and gets a number, so many square inches, let's say, if she does the similar thing on the orange, it's going to come out bigger because the sides bow out. And if she does it on the saddle, it's going to come out smaller because the sides bow in. So this is two ways in which curvature, and I want to say, well, we have a notion of what we mean by curvature. We know an orange is curved, we know a watermelon is curved. But these are ways in which curvature shows itself and can be defined. I'm not defining it, but can be defined in this way. Now, what got this show on the road was shortest curves. So let's pause for a little bit and talk about shortest curves. So we're thinking again about shortest distance. Okay, which curve has the shortest distance along it? Well, remember, distance is speed times time. If the ant knows how fast she walks and has conveniently got a watch, she can figure out what distance is. Now, what about speed? How do you work out speed? Well, suppose this is now me in 3 dimensions and I'm moving. And when I move, I have a velocity. And this velocity is like an arrow. It has a direction which tells you which way my velocity is going. And it also has a size, a length, which is the speed. So the length squared on this is going to be the speed squared. And you've got a rule for doing it, which is Pythagoras. You put in a set of axes, you do this squared plus this squared plus this squared, and that's the length squared of the vector. And that's what feeds into distance. And that's what feeds into the notion of shortest distance. So it's Pythagoras. I want to say in general terms, it's a rule of squares. It could have been something different. It isn't. It's a rule of squares. And I'm going to call this rule the metric. It tells you how long the vector is. And once you know how long the vector is, you can feed it in here and say how long the curve is. So I'm going to call this rule the metric, and I'm always going to write it as a little red g. So think of little red g is your rule for measuring lengths. So it measures lengths. From that, it also measures area. If we're in 3 dimensions, not on the orange, of course, but if we're in 3 dimensions, it will also measure volume. And there's another thing that it does, it measures angles. If you recall a little bit of trigonometry, sines and cosines are ratios of lengths. Well, G measures lengths, so it measures ratios of lengths, so it measures angles. So G does that as well. Now comes the payoff. Suppose we let G vary from point to point. So it could be this in some places, but it could be something else somewhere else. So as you move around, in this case, in your 3-dimensional space, or on your orange, as it may be, if G varies from point to point, then the rule of shortest curves will have to change. It won't be straight lines anymore. It'll have to change. Your shortest curves won't be straight, and you'll have, as we saw on the previous picture, you'll have curvature. So this is where curvature comes from. But beware, because curvature can be singular. Now, singular is a word that mathematicians use to mean bad, and it's the opposite of regular, which is the word they use to mean good. And when you say that something is singular, you almost always mean it's infinite. So there can be places where the curvature becomes infinite. So here's the ant on this rather Baroque thing, which is no longer something as simple as an orange, but imagine it's curved. She can run around on it. And there can be a place where something like this happens. It's like a little Mount Fuji. It comes to a point. And when it comes to a point like that, the curvature has become infinite. It's no longer a nice, smooth, rounded surface where you can think about the curvature. The curvature has become infinite. Well, it's actually not too bad. It's just a single point where there's a problem. You could start thinking of more Baroque examples. Here's a slightly more Baroque example. You could have a very long spike. It's very long, it's got a spike at the end. Well, of course, that's not much worse than this. But once you've got this, you can imagine winding it up and winding it up and winding it up. And now you've got curvature going bad in a rather more complicated fashion. Or you could have a complete nightmare where you have a region on your surface where every point is a spike. Imagine something a bit fractally. You could have singularities everywhere in some region. It could be a complete nightmare. Now, I've just thought of 4 possibilities there. Curvature singularities can be as bad as you can think of, or as bad as I can think of, or as bad as very smart people can think of. So curvature singularities can be an absolute nightmare. So we put that away and save it because it'll pop up again later on. Now I've got a new idea here, and this new idea is conformal rescaling. Now suppose we've got a little bit of a geometry. This is, as it might be, this could be a bit of the surface of the orange, something two-dimensional. I've got a grid of coordinates on it. These are unit distances, if you like. And I could stretch it or I could shrink it. So I could stretch it, it'll look like that. I could shrink it, it'll look like that. But I want to do it in such a way that the angles don't change. So these black lines meet at right angles, so do these, so do these. These are examples of conformal rescaling. If I did this, I've stretched it more one direction than another. Well, this isn't conformal because this angle down here is more than is less than 90, and this one up here is more than 90. So it's not conformal. Now you can do more Baroque and complicated things. You could take this one and the horizontal lines you could bend around into circles, and the other ones going the other way, you can make them into radii. And if you're careful about how you do it, that can still be conformal. Conformal means the angles are preserved, and here they are. We can see these angles are being preserved. Okay. Oh yes, that's right. So now I want to have a little bit of cultural relief. This is a picture by every mathematician's favorite artist, Escher, and it's called Escher's Print Gallery. And if you want to know much more than I'm going to say about it, here's a link that you can go and look at. So if we start in the bottom right, this is evidently a print gallery. There are pictures hanging on walls, they're prints. And as we move over to the left, what's happening? Well, Escher is stretching the picture. He's got a short person here. By the time we get over here, this person is around about four times as tall. And I want to emphasize, it isn't tall, this person isn't tall because it's perspective and they're nearer to us or anything like that. It's Escher that's just flat out stretched the picture. There's a little picture on the wall over here, and it's become a much bigger picture on the wall over here. Now, as we move from bottom left to top left, he's stretched it again. This was one side of the picture. Now it's come all the way here and it's gone off the top, okay? And everything's got stretched again, going from bottom left to top left. And if we go from top left to top right, everything's got stretched again. The picture has a picture of a town in it. The houses of the town have become much bigger. You can see they're bigger. Look at the size of the windows. And it's been stretched about 4 times again. And then when we drop down from top right to bottom right, it's been stretched again. You can see as we move down here, small window, larger window, much larger window. He's stretching it as he moves down here. And then, of course, we're back to the picture gallery. So the picture gallery is inside the picture, which is hanging on the wall of the picture gallery. Now, that's the cleverness of Escher that he's done that. But this stretching, I want to say, is also a conformal rescaling. He's stretched it in a way that preserves the angles. And you can see that if you look at these little bits of wood, which are defining the window panes. Down here, they meet at right angles. By the time you get over here, well, look, they still meet at right angles. They're not straight lines anymore. I mean, this one's bent all over the place. This one's bent all over the place. But where they meet each other, they're meeting each other at right angles. And that carries on. The windows stay rectangular, the windows stay rectangular. This is a conformal stretching. You can do more, as it were, more cute things with this. Now I'm going to show you another Escher picture, which takes a little more description. And this one may very well also be familiar to everybody. This is one of a series that Escher calls the circle limit. And what I want you to imagine is you only care about what's happening inside this circle, which is around the outside of it. And there's a definition of a metric, and remember that means a way of measuring distance that varies from point to point, in which the shortest curves, which are the things that have to replace the straight lines, the shortest curves are these kinds of circles. So you can see one here. I'm tracing it with the cursor. It's a part of a circle and it meets the boundary circle at right angles. You can't see that because the picture gets very blurry there, but take my word for it. Here's another one, a smaller one. It's a circle, a part of a circle. It meets the boundary at right angles. The diameters going right across the middle, they certainly meet the boundary at right angles, and they're like limits, if you like, limits of circles. Now, there's a lot goes into this picture, and a lot one could say about it. But the key is that these black fish, that's what they tend to be called, these black fish in the metric, which is determining these shortest curves as these circles, in that metric, these black fish are all the same size. Now that's not a surprise for these, because obviously they're the same size, but this one is the same size as this one, is the same size as this one, is the same size as this one. As you move to the edge, the apparent size gets smaller, but the size in this metric, which I haven't defined, means that they're all the same. Well, now when you get to the end, obviously they just bunch up and they bunch up and they bunch up, and there are infinitely many of them before you get to the edge. So the edge is infinitely far away as far as the little fish themselves are concerned. But the trick that Escher has pulled, he's done a conformal rescaling, and he's pulled in those things that were infinitely far away, and he's stuck them on the outside as a circle. So here's a clever thing you can do with conformal rescaling. You can pull in something that's infinitely far away and add it on as a boundary. So the boundary circle, I've said it over here, the boundary circle is at infinity, but it's been added on by conformal rescaling. Okay, well, that's just a few introductory bits and pieces about geometry. And now I'm going to move on to my second bullet point, which was special relativity. Now, if you want to get to the bottom of special relativity, you have to understand space-time diagrams. That's the key idea. So here's a space-time diagram. I want you to imagine that what you're seeing at the bottom is a map. So it could be like a page out of your Rand McNally, and you've got north-south is one dimension, and you've got east-west is another dimension. Where you'd like to put the third dimension, you're not allowed to, because I want to make the third dimension to be time. So as you go up the page, time passes. Now this red wiggly line here, that's supposed to represent me moving around in the map. And so the map's down here, and at different times, I'm in different places. So for example, at this time, I go over to the red line, I drop down to the map, I'm there. Whereas at this time, I go over to the red line, I drop down to the map, and I'm there. So as I move around on the map, and I add the time dimension, I get a nice curve through what this now is, which is space-time. I get a nice curve through space-time, and it's called my world line. Now, if you take a place where the world line is almost parallel to time axis, then that means that as time passes, my position doesn't change very much, and that means I'm moving slowly. But if you take a place like this, where it's tipped over a long way from the vertical, then as time passes up here, my position changes quite a lot. So you know my speed by looking at how the slope works on this line. Well, there's a lot more one could say about space-time diagrams, but if you can swallow them, then you can swallow general relativity, special relativity, and then general relativity. So what do you get from special relativity? Well, you get two key ideas, and you should be astonished by the first one of these if you haven't seen it before. Special relativity says the speed of light is the same for all observers. And this should be, if you didn't know this, this should be a surprise. That says I'm in England. If the sun was shining, I could measure the speed of the light coming from the sun, and I get an answer. You're in, let's suppose, Arizona. You're much, much closer to the equator. If the sun's much more likely to be out, and if you measure the speed of light, you will get the same answer as me. And that's notwithstanding the fact that you're near the equator, the Earth is spinning around, so you're moving much faster than I am. If we had a friend up in the International Space Station, they'd be moving even faster. They could measure the speed of light from the sun, but they will get the same answer. The speed of light is the same for all observers. That's the first borrowing for special relativity. The second borrowing is that nothing goes faster than the speed of light. A small number of things can go at the speed of light, including light, of course, but nothing can go faster than it. Well, if we stick that on our picture, at a certain point and at a certain time, I could let out a flash of light, and that flash of light will have a slope which corresponds to the speed of light, and as we move up the page, it will spread out. It spreads out like a ripple on a pond. It actually is a sphere rather than a circle, but you can't get that onto the diagram. And I could keep on doing this. I could have done it back here, and here's a flash spreading out. Here's an earlier one, it's a flash spreading out. There could be one of these everywhere, okay? Anywhere you like, there could be one of these. And the world line, because of the second thing from special relativity, the world line is always inside the cone, okay? So here's the picture of the world, the geometry of the world that you get from special relativity. This is the world according to special relativity. At every event, an event means a point of space-time, a place, a certain place at a certain time, and I've drawn 12 of them. At every event, there could be a cone, okay? They're potentially there, and it's traditional or conventional to draw the past of the cone as well. So that the future bit is the time goes up the page. This is the ripple expanding, but one could imagine an incoming ripple which focuses down to me here. But the point about them is they're all lined up. They're all lined up like soldiers. It's completely rigid. Now, in order to define one of these, I need to know the speed of light. So I need my rule of squares. So I need my metric. So there's a metric hiding behind this picture. Now let's think about how a light ray moves through this universe. Not a flash of light now, but a single light ray, a torch beam. It runs up this cone, gets passed on to the next cone, runs up that cone, gets passed on to the next cone, runs up that cone, and it's a straight line all the way through space-time. So a light ray moves from point to point, always lying on a cone. So therefore on straight lines. And remember our discussion about G, the metric earlier on. This metric is flat because these curves, the light follows shortest paths, these curves are straight. Now here's the world of special relativity. How about the world of general relativity? We want to put gravity into it. Well, what does gravity do to light? Now there's a famous experiment which tells us the answer to this. And so here's the famous experiment. What does gravity do to light? This is very schematic. You want to imagine that this eye represents an observer on the Earth, which I haven't bothered to draw. And this person, we know you absolutely don't look at the sun because it does terrible things to your eyes. So you wait for an eclipse. Now, when there's an eclipse, in the middle here, not to scale, would be the moon. And the moon is just exactly the right size to cover up the sun. So at the eclipse, you look, the sun is covered up, and you can see, well, you do it with photographic plates, you can see stars round, which are close to the sun, as if from where you're looking. And then you look in your star atlas, and you discover that this star, which is apparently here, is actually here. Okay, so you've constructed your star atlas at a different time of the year. You know where the stars actually are, and now at the eclipse, they appear to be further out. So this one is apparently here, actually there, and there's an angle of deflection, and it's because the light from the actual star, as it goes by the sun, its path gets bent by an amount which was predicted by Einstein very early on and measured very early on, and was the first great triumph of general relativity, the light path is not straight. Well, if the light path is not straight, then the light cones aren't lined up like soldiers anymore. And that means that the G isn't what it used to be. What did it used to be? It used to be flat. The G isn't flat. The light cones are not lined up. They're tipped by the proximity of the sun. It's the sun that's doing this. So you've got a great massive mass here, and that's doing the bending. So the light cones are not lined up. They're tipped by the proximity of the sun. And so the picture that you get of the world of general relativity, it starts off like the world of special relativity. It has to be more or less like that because there are regions where there isn't very much gravity. But the world according to general relativity is like this. There's still a cone at every point, and they're still defined by a metric, but they move. They're not lined up. They're tipped in complicated ways. Now, if you do a ray of light, it runs up this cone, it gets passed onto this cone, it gets passed onto this cone. It's following a curve in the space-time. So a ray of light moves on from cone to cone, but it must follow a curved path. And that means the metric is not flat. There is curvature of space-time. So gravity is coded into curvature, even though we don't know the details, or I'm not going to tell you the details. And there's another thing to remember from this picture. When we were back with our first case, the world line of a person, or indeed of anything, a planet, a rock, whatever you like, has to lie inside the cone. It has to lie inside the cone. So by the time we're here, our possibilities of movement are constricted. They have to lie inside the cone. So there's a very nice aphoristic way of talking about general relativity. And this is due to the American physicist John Wheeler. In general relativity, space tells matter how to move, and that's this notion that you've got to stay inside the cone when you move. But on the other hand, it's the sun that tips the cones, so it's matter that tells space how to curve. So this is an aphoristic way of describing general relativity. Now, of course, it's not enough for what we want, because we need an equation, because we want to get quantitative on this. And there is an equation, and it's due to Einstein. So there is an Einstein equation. And this is the second equation that I'm giving you. And just schematically, you have to come up with a measure of curvature, and you have to come up with a measure of the matter content of space-time, where the suns are, where the planets are, and so on and so forth. And the Einstein equation tells you the measure of curvature is Newton's gravitational constant times a measure of matter content. That's it schematically. Okay, so I've summarized general relativity. That was my third bullet point. Now, once you've got general relativity, as I said, you can use it in the solar system. You can get more detailed information about the way the planets move. And always these things come out right. I mean, Einstein basically got it right. There's no doubt about that. And the famous example that's always given now is that your GPS or your sat-nav is as accurate as it is because it takes account of general relativity. The calculations that go into the sat-nav are general relativistic calculations. But you can take the larger view, you can move on and say, well, I'm not just interested in the solar system. Solar system is part of the galaxy, and the galaxy is part of a cluster of galaxies. I can jump up and try and use my Einstein equation to tell me about the universe thought of as a whole. And when you do this, you jump to my fourth bullet point, and my fourth bullet point is cosmology. You want to make models of the universe as a whole. And if the universe as a whole has got three important properties that I'm going to put in here. It's isotropic, and that means that it's the same in all directions. And you can see now why we're going up to large scales. I mean, the solar system is not the same in all directions. In one direction, there's the sun, and in all the other directions, there isn't. The galaxy is not isotropic. There are painted across the sky, there's the Milky Way, and that's the galaxy, and then directions at right angles to that, there isn't the Milky Way, so it's not isotropic. It's only when you get up to the scale of clusters of galaxies that the clusters of galaxies, they're the basic building blocks, and they are distributed in a way which is nearly, I've said here, isotropic. For those of you who know, of course, there's also microwave background, which is really nearly isotropic. The universe is also close to being homogeneous, and what that means is at a fixed time, it's the same on the average at all locations. Again, you have to do some averaging for this because there's a lot of difference between being in the middle of the sun and not being in the middle of the sun. It's the same at all locations on the average. And this is much more difficult as a hypothesis to test, but nonetheless, it has general agreement. And then the crucial novelty here is that the universe is expanding. This is Hubble in the 30s. The clusters of galaxies are moving apart. And what's more, the further apart they are, the faster they're separating. So there's a rate which is increasing with their distance. So we want to make a model, a general relativistic model of a universe which is doing this. And it'll have a metric which depends on time, because after all, the universe is expanding. It's got to depend on time. And so I've got a schematic for what this looks like. This is meant to be a space-time picture. Time is increasing up the page. And what I'm drawing, this blue rectangle, it's 2 dimensions. It's supposed to be the universe at the present time. And of course, the usual problem with space-time diagrams, I have to draw it 2-dimensional, even though I know it's 3-dimensional, because I have to leave room for time on my picture. So this is the universe at present time, and it's this which is homogeneous, i.e. the same at all places on the average, and isotropic, the same in all directions. Well, if it's the same at all places and the same in all directions, then its curvature has, in a certain sense, to be constant. But that constant curvature can vary with time, because here's a future time slice. This is the universe at a future time. And the distances, now I've drawn them as single spiral galaxies, but think of them as clusters. The distances between them have gone up. Down here, they were only this far apart. Up here, they're this far apart. And the further apart they were, the faster they're separating. Okay, so that's the schematic. So you code all that into a metric, you plug it into the Einstein equation, you solve the Einstein equation, and you get quantitative views about what the universe is like. And the interest lies in, or part of the interest lies in, what was it like back in the past, and what's it like up in the future? Oops, I'm trying to hide the thumbnail. What's it like up in the future? Well, the past is easier because as the movie runs up the page, everything's moving apart. So if you run the movie backwards, everything's moving together. And you will discover when you solve the Einstein equations that there was a time in the past, not that long ago, but not that recent either. There was a time in the past when all the matter was in the same place. So into the past, there was a moment of infinite density. And by a more complicated calculation, it was also a moment of infinite temperature. These are properties of the matter density, i.e. the pounds per cubic inch or whatever, the grams per cc, was infinite in the past. Now remember your Einstein equation. Your Einstein equation said a measure of curvature is big G times a measure of matter content. The matter content has become infinite, has gone singular. Well, the curvature must have gone singular. So there's a time back at the beginning where there was a curvature singularity, and we know enough to be a bit scared of curvature singularities. They could they could have been ridiculously complicated. They could have been as complicated as the smartest person could imagine. But, and there's a point that Roger's been making at least since 1975, the singularity at the beginning, which of course is what we traditionally call the Big Bang, was nowhere near as bad as it could have been. It could have been horrendously complicated, and it wasn't. In fact, it seems you can remove it by conformally rescaling the metric. So here's a schematic of the universe. The slices of constant time as we move into the past are getting smaller. Each of them is three-dimensional, but crunch, there comes a point when the dimension drops to zero and everything was in the same place. Now, if you expand each of these, you stretch them out so that this one's the same size as this one, and you stretch it out so this one's the same size as this one, then this point here can be stretched out into something three-dimensional, and it can be a boundary. Instead of just being a singular point, it can be a boundary that you add at time zero. Okay, so this is, now Roger has insisted that the Big Bang had this very special character. Well, it was a subsequent notion that it was a character that you could characterize like this by adding a new boundary, but it's a complete mystery. Why? Why in the world was the Big Bang like that? It could have been horrible. Why wasn't it? Well, let's drop that and go into the future. Into the future, the galaxies are moving apart, so the density is dropping to zero, matter becomes negligible, but the universe also has in it something called dark energy, and the dark energy is driving the universe to expand exponentially fast. Remember, that means however big you are, you're going faster and faster. Now, when that happens, you imagine blowing up a balloon, the balloon gets smoother and smoother and smoother, the curvature smooths out. So we have this schematic of the universe. Here's the Big Bang. Here are the surfaces of constant time, and they're getting bigger exponentially fast as we go up here. And now we do what Escher did with circle limit. We pull the infinity, which is happening out there and out there. We pull that in by conformal rescaling, and we stick a boundary on the top like Escher's circle limit boundary. So our universe, we've made it look like a tin can. It starts at time zero, it goes on to time infinity. It's awkward having time infinity up here. There is a natural other way of defining time, which still starts at 0, but now only goes up to some finite value at the very end, and a new boundary at both ends. And now comes the first of the big surprises. Because you've got dark energy, the boundary that you're adding in the future, the new boundary that you're sticking on at the top, has the same character as the new boundary you're sticking on at the bottom. And when I say the same character, I don't mean it's exactly the same. I mean, it's the same kind of thing as regards curvature. And this is a conformal property because the one at the top is infinitely big, so we've infinitely shrunk it, and the one at the bottom was infinitely small, and so we've infinitely expanded it. That's to remind ourselves of this picture here. And so now we're ready for Roger's outrageous suggestion, which is stick them together. So you imagine this is a whole eon of universe from its Big Bang, which I've stretched out, to its infinite future, which I've pulled in, I've scrunched in, and it's got the right character, that infinite future has the right character to be the Big Bang of another eon. And the next eon can go all the way through to its infinite future, which I've scrunched in, and again, it has the right character to be a Big Bang. The metric isn't like this, because the metric is going, let's look at the bottom one, the metric is going from infinitely small to infinitely big to infinitely small to infinitely big to infinitely small. It's the conformal metric, that bit of the metric which will tell you about angles and so on, that is perfectly well behaved as you go right through these things, no singularities at all. So the conformal metric is cyclic. This is why it's cyclic conformal cosmology. It's not periodic. There's no suggestion that every, this is like a bamboo cane, there's no suggestion that every bit is exactly the same as every other bit. It's cyclic, it has similar features. But now, if this is a real model of the universe, if we're in this eon, we have another eon coming after us, we had another eon coming before us, you could now imagine that stuff can come through from one eon to another. Stuff, well, that's going to mean radiation. It could be electromagnetic radiation, it could be gravitational radiation, it could be magnetic fields, but stuff can come through from one eon to the next. And it's the detection of that stuff by which the conformal cyclic cosmology will stand or fall. Now, I think that's exactly 40 minutes, so I'm going to stop there, but I will say happy birthday, Roger, and thank you for conformal cyclic cosmology.
Well, thank you, Paul, for a wonderful, beautifully clear talk. I think that everybody is just in just the right position to understand the following talks. I think you've done it, as always, extremely nicely.
That was a great talk, Paul. Thank you so much.
Thank you. Thank you.
Yes. Okay, now who's next? Actually, Stuart, I'm sorry, I came into this without
Brian Keating.
It's Brian. Okay, great. Okay.
Hi, Roger.
Hello.
Hi, everybody. Good to be with you.
No, well, Brian, I remember from San Diego, and he runs this wonderful. Well, I don't know what the stage. You can explain it to us, I guess. Your telescope, and you'll tell us how it's set up, and not in San Diego, but is this Chile? I've forgotten where you are in this.
There's two. There's one in the South Pole, Antarctica, which I'll talk about primarily today, and at the end, I'll talk about the Simons Observatory at the end in Chile.
Okay, so one of them is in Chile and the other is South Pole. Great. Well, let's hear about them and how that relates to observations, which might connect with what Paul was saying. Let's see how it goes.
Great. So can you see my shared screen?
Yes, I can.
Wishing Roger a happy 3 billion seconds, and to at least 1 billion more, he'll reach the biblical age of Moses at 120 years if he hits 4 billion. So we're all pulling for you, Roger. We want to reconvene in another 30 years. It's a delight to speak, and I have some gifts. So I have established a YouTube channel where I am presenting interviews, conversations with Roger and other illustrious guests, and even revisiting and visiting some of the most vexing issues in cosmology that for the first time I claim in human history, we'll be able to do things that the ancients, the philosophers, the theologians wish they could have done. And I'll explain what I mean as I go along. So you should see a picture now. It says, "Let there be light" with the Big Bang and an asterisk. You guys see that? Okay, great. So, of course, we in the Western Hemisphere and Judeo-Christian traditions think about the universe as an origin point, as perhaps a singular moment, perhaps when time itself began, as Stephen's late great colleague as Roger's late great colleague Stephen Hawking would talk about. And we'll talk about Stephen Hawking briefly here, but this is Roger's Big Bang. And so I thought, we should have some cake. And I thank Stuart and all the organizers for doing it. Now, when I put this together and took a picture in my laboratory here at UC San Diego, I got a fire alarm that went off for this reason. There's too many birthday candles. But I do hope, as I say, we can celebrate the biblical age of 120. Now, I mentioned the Bible, and it's kind of interesting. I've noted that in previous conversations that the Bible, the Old Testament, the Torah, as we call it in Judaism, starts with the Big Bang. It starts with the origin of the universe. God created in the beginning, single beginning, and goes on to describe things. Now, this is a book about a certain nomadic tribe of Semites wandering through the desert. Why would it start with the beginning of the universe? And that's actually a very, very puzzling question. And I always like to think that the origin of something is a very incredible and unique point in that organisms or persons or individuals or organizations' life. And just like Roger's, we're celebrating his origin. And the question that I asked is, was there a origin? In other words, was there a singular origin of the universe? That is perhaps the most puzzling, mysterious, delightful question that could be asked. And we are actually in the position to prove it, or perhaps even falsify the biblical narrative and even these alternatives that I'll get into with modern technology that my colleagues and I are building around the world and even in space. So that's the stakes. The stakes could not be higher. We're talking about the origin of all things. as we talk and celebrate Roger's origin. And speaking of books, Roger's endorsement, his encomium on the back of my book, Losing the Nobel Prize, did not cost him a Nobel Prize, thank goodness. And I always hated this idea of dust jackets. I don't know. I got Roger's book, The Emperor's New Mind, in paperback when I was a wee lad, as you say. And I have it ever since. And it hasn't been damaged or anything because there's no book cover to lose. And I used to hate these book covers. They fall off, they get covered in dust. And how much dust is like raining down on books anyway that one needs an actual physical cover? But nevertheless, I do treasure the blurb, the encomium that Sir Roger wrote on the back of my first book. I have a new book coming out in just a month called Think Like a Nobel Prize Winner. And Roger is one of the main characters. It's drawn from my 9 interviews with Nobel laureates over the past year on my podcast entitled Into the Impossible, which I run here as co-director of the Arthur C. Clarke Center for Human Imagination, where Roger has spoken many, many times, and we hope to have him back, as I say. So are there alternatives to a single Big Bang? And I like that Paul, went really old school and used transparencies. I was a late convert to PowerPoint and Keynote, so I'll make up for technologically what he lacked, so to speak. So there'll be a lot of slides, but hopefully in the review of the video, people can dig into more detail or contact me if they have questions. So are there alternatives to one single Big Bang? Yes, there's many of them. And of course, we're here to talk in this session about maybe cyclic cosmology and others, but I want to point out there are other alternatives to a single event in space and time, as we are kind of inculcated with in our mother's milk, so to speak, as young practicing cosmologists. And one connects very directly to me here at UC San Diego, and that's known as quasi-steady state cosmology. I'll talk about that in a minute. I want to talk about bouncing cosmological models, which are the brainchild of Neil Turok, Paul Steinhardt, Anna Aegis, and many others. And there's a tremendous amount of research going into those models. Of course, the inflationary multiverse predicts the perhaps semi-eternal, semi-infinite extension of universes nucleating from nothing, going on perpetually into the future. So that is a contrast to a single Big Bang origin. We have Roger's theory, and we also have a big crunch, which may have been semi-infinite as well in both directions, or, so infinite, but there may have been only one crunch. There could be multiple crunches. And Roger, in some way, has touched upon almost all of these models. And for that reason, I want to recognize it. And for the fact that it has a certain prejudice in my mind, in a good sense, which is the lack of a quality that those other models have. So Roger and many others have pointed out that the problem of entropy in a collapsing universe. We're not going to talk too much about that. And I want to, assure people that this model is not really so appreciated. Although I want to point out that in the Penzias and Wilson's famous 1965 paper, where they declared the detection of thermal radiation of a black body nature at 4,500 megacycles, that observation was accompanied by a paper with by Robert Dickey, Jim Peebles, David Wilkinson, and Roll. And that paper, they never once mentioned the Big Bang. It's not mentioned at all in that paper. In fact, they talk about the existence of a previous cycle, suggesting so much as to go as far as almost a collapse, a singular origin in this sense. So not a Big Bang, but actually the result, the fireball that they observed, the aftermath thereof, was actually the result of the previous cycle in the universe's history. So we don't believe that this is Tolman and others had suggested this could be a legitimate way to avoid a single semi-infinite expansion of the universe from a singularity. This is no longer in favor by any practicing cosmologist for many reasons, but one of which is the problem of entropy buildup and the classical thermodynamic analysis of a single Big Bang collapse. Now, my late great colleague, who I'm privileged to have his office at UC San Diego, I don't smoke cigars in that office, But yeah, Jeff Burbidge was a titan of cosmology, along with his phenomenal preternaturally gifted wife, Margaret, who passed away just last year at age 100. They were friends, they were colleagues, and Jeff maintained till his dying day the validity of a model of cosmology, which went from being called a steady state cosmology to a quasi steady state cosmology. So whenever you have a prefix in front of something, you have to ask questions about what is the nature of that prefix? Why was it added? Why was it sort of an epicycle added to an epicycle? And that's to take care of things that people knew about from the time of Tolman and others. This problem of both creation of energy and matter in an infinite space that's eternal, but also having to collapse on periods of less than trillions of years in order to form enough of the elements on the left side at the top left of the periodic table. And in order to do so, they required this creation field, and this is the sort of the helium abundance cycling through, and it goes past infinite to negative infinity in the scale, and it goes positive infinity as well. And of course, many people believe that this is ridiculous, this is ruled out, et cetera, et cetera. But many people, including the great Jayant Narlikar, who was Fred Hoyle's student at Cambridge, was on my channel earlier this year. He still maintains the validity of aspects of this model and rightfully points out some of the challenges and some of the things that they presaged, namely a creation field, a scalar field, which finds its way into almost all alternatives to the Big Bang, except for one. And you can guess what that one field is, that one theory is. It's Sir Roger's conformal cyclic cosmology. It's the only one of these models that lacks the necessity for a scalar field heretofore unobserved. Now, why were these things so popular? So Steven Weinberg, recently deceased, the late great Steven Weinberg, said it is philosophically the most attractive model, the steady state, by which he meant at that time it was the quasi-steady state, because it least resembles the account given in Genesis. So Ed Hoyle used to say things like the cosmologists of his time were adopting the Big Bang because they were, quote, overwhelmed by Genesis 1:1. Which is kind of laughable to think that cosmologists would be somehow much more religious and theological than we actually are. But nevertheless, Stephen points out here in this quote that it is a truism that this theory least resembles Genesis. Therefore, if something like an alternative to the Big Bang could be discovered, like steady state, like CCC, like a bouncing model, that would essentially invalidate the account given in Genesis. In other words, a quest of 2 millennia, at least in length. We'll talk about conformal cyclic cosmology. Paul Todd gave a great overview. I really appreciate that. I don't have to go into the details of it. I can save my energy and attention for experiments. But I don't want to leave the philosophical and theoretical. I want to point out that just like Roger's birthday, he doesn't look a day over 2,999,000 seconds old, but nevertheless, these theories are celebrating actually 3,000 years, perhaps, of eminence and of somewhat conscious and implantation in our consciousness. This is from the Book of the Dead of Kennu Mose. I don't know if I'm pronouncing that right. I hope Kennu Mose has a very high H index because this model that is proposed is sort of representative of the cyclic cosmology that finds its way. Some of its DNA is found in Roger's cosmology. So a cyclic eternal universe. This is older in some sense than the biblical narrative of Genesis 1:1. So that is fascinating to me. And it gives me the impetus to study what I do. Most of what I do is, turning screwdrivers, looking at oscilloscopes, soldering resistors. And actually, I'm not doing much of that. My grad students, brilliant grad students are. But I rarely get the chance to really think about the big picture. Why am I doing what I'm doing? And it's to answer these age-old, timeless, philosophical, perhaps, yes, theological questions that give meaning to life and give meaning to my job as a cosmologist. My friend Paul Steinhardt and Anna Aegis have done great work on what's known as the big bounce or bouncing cosmological models, where a universe goes through perhaps infinite, perhaps just one cycle from collapse. But the collapse doesn't have to be to a singular point. It doesn't require, in the new versions that they've come out with over the last 2 or 3 years, they don't even require quantum gravity. And that's very attractive because, as I debated with Roger after he won the Nobel Prize on my podcast, the only two regimes where we tell ourselves this story that we need quantum gravity is at the singularity of a black hole and at the origin of time and space itself in the Big Bang. But both of those are forbidden and prevented from our view via event horizons that Roger and Stephen and others worked out and proved. So we can't, in principle, observe such events. So why do we say so steadfastly that we must have a theory of quantum gravity? I say that rather provocatively. I would, of course, be very interested in it if it did exist, but it's noteworthy to point out that this model and Roger's model don't require a quantum gravitational solution. So we don't need a grand unified theory or even certainly a theory of everything in order to assess the cosmological implications, as we do with the Big Bang if it's a singularity. So here's an animation from Quantum Magazine of a universe with stuff in it, oscillating in and out. It looks like it goes to a singularity, but trust me, it goes only to 1 pixel, which is in not quite infinitesimal volume. So I did an interview. I did a solo episode on my podcast channel. You can find it there.
One of the most vexing aspects of science is that for every problem you solve,
can see that.
Sometimes you create 2 more problems.
So I talk about the bouncing model and what requirements it puts on cosmological observations. So please do check that out. And I am making a video, an analogous video solo episode. I do interviews and solo episodes. And the solo episode I'm going to do next is about Roger's conformal cyclic cosmology as a birthday present in the coming weeks. The last alternative that I'm going to spend quite a bit of time on for one reason alone, in that it has guided the experimental quest that I and my colleagues are embarking on to measure waves of gravity imprinted on the last scattering surface of the CMB. And that's the eternal inflationary multiverse, where the two men most associated with its existence, Alan Guth and Andre Linde, have both said more or less that if you measure in evidence for inflation, it brings us much closer to the reality of the multiverse. And of course, Andre Linde has said things like he'll bet his life on the existence of the multiverse. In another video I did, I pointed out he said things like, should there only be one universe? You must prove that there's one universe instead of a multiverse. The stakes, again, could not be higher. And of course, Rogers pointed out a lot of the lacunae in the theory of inflation, and we'll get to that. But the contradistinction between inflationary multiverse and a single Big Bang is just that you can have multiple universes beginning at multiple times in multiple spaces. You can have parallel universes in a certain mathematical sense, as Max Tegmark has talked about, et cetera, et cetera. So this is another alternative to a single Big Bang. That's the title of my talk. So we always, at some point, because I believe that physicists have a deep, abiding mathematician envy, and that is because in mathematics, one can prove the limits or lack thereof, as Roger talked about, of the completeness theorem. Gödel's incompleteness theorem can show you the limits of a formal axiomatic system. We don't have such a criterion in physics. And we would like to think of ourselves as practicing the most fundamental foundational aspect of science. And yet we lack this ability to say what falls outside the rule of physics. Now, most people take Karl Popper's dictum, his demarcation hypothesis, as sacrosanct, but it's not. There are many, many alternatives to Popper's demarcation, but nevertheless, it's a good guide. And in fact, Popper believed in the steady state model, or actually supported it for many reasons, one of which was that it had the ability to be falsified. And he even felt that even knowing that a theory was wrong, you should still keep it around for some time. And I've pointed out in conversations I've had with luminaries on my channel that imagine if Twitter existed in 1864 when a young Scotsman, James Clerk Maxwell, was coming up with these 4 equations that would later bear his name. Now, there was no evidence for this at that point, electromagnetic waves, et cetera. And yet he had to establish these fundamentally correct foundational laws of unification. He established them based upon a model of essentially an ether replete with microscopic gears and vortices and whirls and so forth. So imagine Twitter exists back then. You would have said, though, that theory can't be right. It must be falsified because we don't have evidence for these microscopic whirls and gears and so forth, as we know now, of course. And so you might throw the so-called baby out with the bathwater. So don't take falsifiability as a sine qua non. And I actually add a corollary, Keating's razor, that you shouldn't add stuff that you can't falsify to an already falsifiable theory. In other words, let's look at these 4 different alternatives that I've discussed. I lift out the big crunch because it's no longer really pursued. So look at quasi-steady state cosmology. Is it falsifiable? Yes, it is. Is the bouncing universe falsifiable? Yes, it is. And I'll explain how. Is conformal cyclic cosmology falsifiable? Yes. Is the inflationary multiverse falsifiable? No. And even its proponents will admit that you can't falsify it. You could only motivate it, perhaps not even prove it by circumstantial evidence that I'm about to describe. Now, on the third column, I put in, do these 4 theories require the existence of a new scalar field? And sui generis among them is conformal cyclic cosmology, which does not rely on a scalar field. In other words, even the bouncing model, which has probably the most common ancestor, the earliest common ancestor in Darwinian language, to conformal cyclic cosmology. And obviously Paul and Roger are good friends and influential. Roger's influenced Paul as well. But the existence of a new scalar field, both in quasi-steady state cosmology, in bouncing cosmology, and in the inflationary multiverse, are distinguished. So that's a fact I don't think many people point out, that this field, which you can't falsify necessarily, because it has certain properties that turn it on and off at epochs invisible to our instruments. But Roger doesn't require that. Doesn't mean Roger's right, and we'll talk about that. But Roger's the only one on this table, at least, that gets 2 green marks, and green meaning yes and falsifiable, and no scalar field meaning no, in Keating's corollary. Now, so how can we falsify those 3 models? Well, you can use CMB polarization to do so. So we invented, my colleagues and I, in 2001, it's the 20th anniversary of inventing the BICEP series of experiments when I was a postdoc at Caltech with my late advisor, Andrew Lang. And we realized, based on work of Alexander Polnarev at Queen Mary and later Mark Kamiankowski, Arthur Kozowski, Matthias Aldariaga, Arthur Seljak, and others, that you could have a distinct, clear imprimatur of inflation if it took place, and if inflation took place at a substantially high enough energy range at an early time, say 10 to the minus 37 seconds, after what we don't know. It could be the collapse of a previous cycle. It could be the creation of time itself. But it's not the Big Bangs. People sometimes conflate inflation with the Big Bang origin of time. It's not. It occurs after, some 10 to the 6 Planck times after the origin of time, at least as we think about it. Leads to a pattern of temperature fluctuations, which later produced the large-scale structure that we see. But there's another prediction of inflation, in fact, that is robust in all models, that inflation should predict a background, a gas almost of a background suffusing the universe with gravitational wave energy. Those gravitational waves, like photons, live forever. They live long enough to shake up the surface of last scattering. And when they shake up the surface of last scattering, they endow it with shear and stress. And the stress energy tensor at last scattering will produce this twisting, curling pattern of microwaves that we call microwave polarization, that we call B-mode polarization. So it becomes a crisp test. If you see the inflationary gravitational wave B-mode imprimatur, then you can claim evidence for, not proof, but evidence of inflation, which again, according to Guth and Linde and many others, means evidence of the multiverse. Again, the stakes could not be higher. I set out to do this in 2001 with my colleagues at Caltech to build a Galilean refracting telescope. A small telescope is all that you need. You don't need an enormous 10-meter, 30-meter telescope like my colleagues are trying to build around the world. You only need a small telescope, but the key is, and it could be a refractor, just like Galileo used 409 years ago this month, 411 years ago this month, and he used it to observe things that in the heavens that were formerly thought to be impossible. And our telescope is really quite simple. It's cooled entirely using isotopes or liquid helium itself. Cooling it down below the 3 Kelvin background is actually the coolest telescope in the world. The entire telescope is cooled below the temperature of the CMB, or the detectors are cooled below the temperature of the CMB. These are these magical detectors built by Jamie Bach at JPL. They're superconducting sensors. I won't get into great detail about that. I should have a video on that on my channel. Here's an illustration from Wayne Hugh, a friend and colleague at University of Chicago, showing that when you have anisotropic photons in the upper right, the thing that looks like this peanut orbital. You can have different a cloverleaf orbital. You can have a unique pattern called B-mode polarization, which produces this parity asymmetric, not mirror symmetric pattern of microwave polarization. So what we said is we'll build a polarimeter, we'll go out and we'll measure it. And this is what the polarimeter looked like, called BICEP 2, and it had the ability to rotate on its axis about the symmetry axis of the telescope to see if polarization modulates as the spin one field should, so twice for every physical rotation. That's the characteristic of polarization. And then we just point it in every spot in the sky that's clean, or so we hoped, and we will get a map of polarization, just like the temperature anisotropy map, Planck and WMAP, et cetera. It's a small telescope, only 10 feet tall, and we took it to a special place. I would have loved to stay here in San Diego, but we had to take it to one of the highest, driest places on Earth because water absorbs microwaves. It's been the site of exploration for over 110 years. Famously, Robert Scott got there second. His team, they all died. And he said, "Great God, this is an awful place." And all the more so for having reached it without the benefit of priority. It's still very dangerous, as these videos show. So if you go there, be careful. There are dangerous creatures there. And you might think, well, maybe penguins just hate each other, like, faculty meetings sometimes devolve into. But actually, they don't like people either. So don't try to take one home with you, as that video shows. And as we go there now, we're escorted in luxury by the United States Air Force. And we ski in and ski out on a ski plane. And we have a spacious accommodation. So there's no danger of freezing to death here. And you have to take a selfie and put it on Instagram once you get there. And when you do, you go to work, and the building on the left, the second most important building at the South Pole, next to the outhouse. Yeah, that's the most important place. You see the building is built up on stilts to prevent the accumulation of snow, which otherwise would swallow up the building in about a decade. So this has been there since we installed BICEP 2. And our team went there in 2005 and we installed it, and it's been operating more or less continuously for the last 16 years and is now actually in a fourth generation called BICEP Array. So on March 17, 2014, around the world, we made headlines because we claimed the detection of B-mode polarization, the harbinger of inflation, the hallmark of the multiverse, perhaps. And there were headlines around the world speaking about our shoo-in for the Nobel Prize. And remember, the model that you should have in your mind is that if inflation took place, then gravitational waves are produced, and those gravitational waves produce a twisting pattern of microwaves called B-mode polarization. So that's an image from the Washington Post in America, and just a cartoon that they published on that day. And now compare that to our actual data. It's identical. This is our real data showing unequivocal evidence for twisting, curling pattern of microwaves. And of course, this, as I said, made headlines around the world. In the newspaper of record, the one that prints all the news fit to print, the Union Tribune here in San Diego. No, the New York Times had this above the fold, as they say, space ripples seen as Big Bang smoking gun. And this was featured on television. So they didn't do it live interviews at the South Pole, but they did interviews with team members and other theoreticians around the world, all of which breathlessly were describing that we would have detected the origin of, and in some sense, the multiverse. There were many headlines about that. And so the debates went on. And actually, soon after this, not so soon, but actually relatively later, some of the folks on the panel today, Roger and Krzysztof, had a paper. And in the paper, they also claim that the B-mode location for BICEP 2 at the very bottom is one of these anomalous Hawking points. This is the first edition of their paper. And I want to say more about that later, what we can possibly say, and why this didn't make it into the final copy of the paper is something of great interest to me, and what we will conclude with, and sort of a ironic birthday present. So all the while, we knew about the aspect that these two people are wondering about, how beautiful the cosmos is, but there's a lot of interstellar dust. Sidney Harris cartoon. And soon after, almost immediately after our conversation, we got complaints that we had detected synchrotron radiation. Now we've ruled that out. We had detected, contamination. Maybe we had detected really these Hawking points or some magnetic anomalies, et cetera, et cetera. So there are many, many hypotheses. But one that always plagued us was the existence of dust. We know dust exists in the solar system. We know dust exists around our kids. We know dust exists in the galaxy and even in extragalactic instantiation of dust. So we knew about that. We didn't have the capability because BICEP 2 worked at a single frequency. We only had one color and two polarization states to deal with. And that was a fundamental limitation because in the end, we could not rule out that the preponderance, perhaps the dominant source of our B mode signal was not cosmological. It was astrophysical. It wasn't a blunder. We didn't leave the lens cap on. We didn't not plug in a GPS, fiber optic cable and mistake neutrinos for those moving faster than the speed of light. None of that. It was an actual honest to goodness measurement that still stands as an exquisite measurement of B mode polarization, but not primordial B mode polarization. So what we found is that the universe, far from what Galileo saw out to the realm of the Pleiades and beyond, perhaps, or Hubble and to Andromeda and clusters of galaxies, and even to the CMB itself, we couldn't see it so clearly. We are basically suffused by a cosmic background or a local background of dust. And that means to do better, we have to abide that our gold did not stay, at least for me. And so we eventually our cosmic dreams, as they say, were blown as dust in the wind. And the question became right after that, after we co-wrote a paper with the Planck team, ruling out the initial claim of inflationary B mode polarization, and instead settling for the more likely explanation, as I say, which still stands at many, almost 10 sigma, the detection that we made, or at least 7 sigma, the detection that we made of B mode polarization of astrophysical, but not cosmological origin. So we must, as Gandhi said, be humbler than the dust in order to seek truth. So you have to build an experiment that incorporates fundamentally an ability to deal with dust. And so the BICEP array team is doing this, and we on the Simons Observatory are doing this as well. It's a large collaboration, not in the South Pole, not in Antarctica, but in the Atacama. So this is our site in Chile. This is a lovely drone shot, which shows currently the Simons Array telescopes on the left, the ACT telescope in the foreground, and the CLASS telescope sort of in the right foreground. And then the far foreground, you can see these little white dots. That's the ALMA Observatory. So we're almost a few hundred meters above their elevation. It's reputedly the driest desert on Earth. I'll show you some videos that give me a little bit of skepticism that that's actually true, because it does sort of not rain, but it does sort of have much more precipitation than I would have liked. Let me see here. So the Simons Foundation, the Heising-Simons Foundation, and our 45 member institutions all contribute in kind, in cash support. Obviously is led by the Simons Foundation. And this is the same Simons of Chern-Simons fame. And that will come into play at Roger's next birthday when we talk about looking for Lorentz invariance violation and cosmic birefringence. It's called Chern-Simons cosmic birefringence, related to axions and all sorts of other stuff that I can talk about when Roger turns 4 billion seconds old. Now, this project is a huge team. This is from 2 years ago. We haven't been in person like this in 2 years, but next year we'll be back here in San Diego. This is from our meeting at Berkeley. What's our goal? Our goal is to measure primordial CMB B modes, if they exist, lensing of CMB signals, gravitational lensing that Paul talked about, and also galactic foregrounds and extragalactic primordial magnetic fields, but also to measure dust. And we do so by measuring not with one frequency as BICEP 2 did, but with multiple frequencies, actually with 6 frequencies. So here's the schematic for this project. It was put on hold, obviously, due to the pandemic, but it's roaring back to life. And it's quite exciting to see all the progress that we've made. It's comprised of 3 telescopes, each one about 40 times more powerful than BICEP 2, also operating in 2 colors, 2 frequencies simultaneously, either 30 and 40, 90, 150, or 220, 270 gigahertz for dust mitigation. And then there's a giant telescope, a 6-meter diameter telescope called creatively the Large Aperture Telescope, with a cryostat that is held under vacuum at 100 millikelvin, that is big enough for my kid to sit on my back and stay inside of and stand inside of, as you'll see. This is huge technology. It's the biggest observatory of its kind. It's a $100 million class project, is fully funded, and we are planning for observations in first light in 2023. The big telescope, as I said, is enormous, 6-meter mirrors that operate in what's called the cross-dragon condition that minimizes polarization systematics. This camera is primarily going to look for E modes and B modes, but B modes, not primordial B modes, but B modes from gravitational lensing in a deep search for relic neutrinos and even for relativistic particles beyond the 3 known neutrinos. So that is one of the unique science goals of a small resolution, large aperture telescope. It's a whole building that effectively rotates on that axis, 15 meters tall, with this multi-ton, 4-ton cryostat inside that weighs more than most cars. So there it is. Here's some people for scale. This thing is just enormous, and it has the capacity for over 100,000 detectors. So 500 more 5 times more detectors than BICEP 2. It's just an incredible instrument. This one is led by my colleague and friend at Penn, Mark Devlin, and his team there, and they have already cooled down the telescopes. My colleague Adrian Lee at UC Berkeley leads the construction of these 3 small aperture telescopes. They're bigger than BICEP, but they're still considered small compared to the large aperture telescope. But you don't need a big telescope to measure B modes. You can do it with a telescope that has worse resolution than the size of the moon, effectively, because B modes are actually 2 degrees and more on the sky. Here in my lab in San Diego, where Roger was just about a year ago, we're showing progress here. Just an advertisement for Dr. Nick Galitsky, who is a heroic postdoc in my group and is on the job market. He's a renowned experimentalist in the field, and contact me if you happen to have an opening for when his postdoc employment ends next year. So these incredible men and women are building this most advanced telescope of its kind to take down and put on this mountain in Chile. Here's it for scale with a person. And all of this is enabled by the detector technology led by my colleague and current spokesperson of the Simons Observatory, Professor Suzanne Staggs at Princeton. Her team is designing these incredible detectors that work at multiple frequencies simultaneously. So they're dual polarization, dual color detectors, which is extremely challenging technically. Not only that, but we have to build thousands of them on a single hexagonal wafer, and then put 7 of these hexagonal wafers in a focal plate. So this is a challenge to build. Our first deployment will have 30,000 detectors in the small telescope, and it will have an equal number in the large telescope. So she's building 60,000 detectors, which doesn't mean you build 60,000 because they never all work at once perfectly. So she has to build more, test them. It's a huge challenge. And then to read out all of these detectors, 30,000 detectors in the large telescope, requires heroic effort in minimizing and doing what's known as multiplexing. So minimizing the amount of cryogenic loading requires that you put as many signals on a single cable as possible. And she's found ingenious ways to do that. So site progress continues. We've poured foundations for the telescope platform for the 3 small telescopes. Here's a concrete pour a couple months ago. You see it snowing. Shouldn't do that in the driest desert on Earth. But we poured these 3 footings. You can see them now. This is big science. This is the biggest project ever undertaken in the CMB field. It will have more detectors in just the 3 small aperture telescopes than were ever used in the entire integrated history of the CMB. Now, let's go back. I said we can't prove that inflation took place, because even if you measure these gravitational waves, it's not clear which of the inflationary models you're choosing. If the multiverse is true, there's literally an infinite number of possibilities. This is something that Rogers pointed out as well. But even if inflation did take place, it may not have had enough energy taken place at high enough energies to produce gravitational waves that are detectable. And there's a very narrow window. I don't mean because of technology. I mean, just the physical vibration of space-time may be insufficient to ever be detectable by even a perfect or cosmic variance limited instrument. So what would we do then? And I answered this question in part in my contribution, Michael Shermer's magazine Skeptic cover article a couple months ago, was about basically, if you can't falsify, do you just rely on social proof? Refer people to that article for more information. So inflation predicts a multiverse, essentially. It comes concomitant with it. String theory does too. There might be 10 to the 500, or maybe an infinite number of universes. Max Tegmark has worked out the kind of minimal number of universes that one could have in order to have infinite effective outcomes in all quantum measurements in his book, Our Mathematical Universe. So as Roger always says, what's the what about that mastodon in the room? And I think it comes back to this in the beginning statement that the multiverse really solves the weak anthropic principle, or addresses it via this infinitude of unseen universes, as Paul Davies, my friend and colleague, says, and one of the originators of Bunch-Davies vacuum and many other things, that we may be just dressing up the mastodon or putting lipstick on the pig, as we say here on the farm. So it requires almost the same leap of faith. And I did a video about that, the faith of a physicist. So last thing I want to point out, this connection to entropy. Roger pointed this out decades ago, and it's fascinating. We all think of time as progressing in one way. We don't see eggs uncracking. Here's some of my exploits in making omelets. But so there's basically two alternatives. One, the universe has a boundary in time, a beginning point. That would be commensurate with the Big Bang. That requires a singularity, perhaps quantum gravity. And you must impose the low entropy state in order for it to evolve, as Roger pointed out decades ago. So that's a problem. That's a challenge. Now, the universe could be eternal. It could be semi-eternal. In other words, it could have extension to the future only. It could have a single crunch, or a single collapse, a single bounce. And then how do you handle the entropy? Well, as Paul said, and as Roger's spoken about, while curvature, perhaps you could have a bounce. That bouncing doesn't require the radical, compression that Tolman's universe did. It's actually very, very slight. And so the entropy shedding that's required to sump away the entropy buildup from cycle to cycle is actually incredibly small, according to Anna Aegis and Paul Steinhardt. And so you might not even need, you could do it all with classical GR, and that's a bonus. The negative, as I said, is it requires a scalar field, which we don't know of any instantiation of other than the Higgs. So I think this is a good point to kind of conclude on where are the cracks in the cosmic egg. As Roger pointed out, we saw this illustration the other day. It's sort of like, as Paul Steinhardt says in this thing, that the probability, the configuration that Roger came to decades ago, presciently, was that obtaining a flat universe without inflation is much more likely than with inflation by a power of 10 to the googol. And there's just a cartoon of that Paul showing in his article in Scientific American. So that's the initial conditions problem. So I want to conclude with some birthday presents, but maybe Roger won't be so happy opening them. But this paper came out last year in May, or was published last year. So apparent evidence for Hawking points. It was not without controversy. I'll just point out that we had Roger in the lab here. There's Nick Galitsky, the star postdoc in my group. I'm holding The Emperor's New Mind, my copy from 1989 when I was a wee high school student. That got me interested in writing books. And it's such a delight that Roger, that you wrote my encomium blurb on the back of my first book. And you're a featured star in my next book, Think Like a Nobel Prize winner. At any rate, here we are. And just a few weeks later, the global pandemic set in. So never, as I say, invite a theorist into the laboratory. It's very dangerous. We know now that Roger's group, and we'll hear more about this, claims of detections of these Hawking points. How could they fit in? What evidence do we have for that? Hopefully we'll hear from Vahe more about this in a moment. I'll point out Roger has that there is already imprint of Stephen Hawking on the sky by chance occurrence. And the question is, are these accepted? Are these Hawking points accepted? So I'll be interested to hear what Vahe says, but I just want to point out that there are claims from at least the first article from the 2018 submission in a paper by Zhao and Scott in 2019 that they claim no evidence at this little more than 1 sigma level, that there's no statistical significant evidence for the presence of Hawking points. They even do what's called the stacking analysis, which I've encouraged Roger to do, and to rely not on the images, but actually on the maps. And again, I'm very much looking forward to Vahe's talk. They also said and discussed the impact and import of polarization on ruling out, verifying, or falsifying the model of conformal cyclic cosmology and Hawking points. So I think it's absolutely fascinating. We have other tools. It's not just the temperature maps, and I'm hoping to have future conversations, as I say, with Vahe and Roger and others. So again, let's conclude. These things have challenges. These models have challenges. Both the single Big Bang and even conformal cyclic cosmology has its challenges. But I think it's a brilliant and most beautiful time to be alive as a cosmologist, to look for signals that have the greatest possible impact on what science and what we're interested in. So I'll conclude with Roger's birthday invocation from his fellow Brit, Winston Churchill, who said, "This is not the end. It's not even the beginning of the end, but it is perhaps the end of the beginning." So Roger, please keep searching for those Hawking points. Never let go of that wonderful spirit that inspires millions around the world. And I wish you the absolute happiest of birthdays. Thank you.
Well, thank you very much. I should mention that I hope some people will look in CCC, because you should see things like B modes.
Yes.
When you look at magnetic fields and how they come across from one eon to the next.
That's
but
right.
This is a detailed discussion, which I hope somebody will do at some point.
Absolutely.
Thank you very much for the talk, and lots of potential there. Let's move on to the next talk, which is Krzysztof. I'm glad to hear that you're talking about CCC and that we collaborated on a paper, particularly the one in the monthly notice of the Royal Astronomical Society, which came up, I suppose, about a year ago now.
Yes.
Yes, and the only criticism I've seen was of a precursor to this paper. Maybe you'll mention that. I haven't seen any after it came out. Maybe there were criticisms of some sort. So anyway, let's hear what you have to say. I'm looking forward to that greatly.
Okay. So thank you very much, Roger. All the best for your birthday. And I will talk about black holes and the CCC, the Cyclic Conformal Cosmology. So this subject that we work together with Roger. I will start with Albert Einstein. The most incomprehensible thing about the world is that it is comprehensible. And it is a very deep statement. It is comprehensible, at least for Roger. So that's the photo in Oxford 2016. So let's start with some introductions of physics. Around 100 years ago, two fundamental physical theories were created, the general relativity. And these two dates are one of the most important. The 25th of November, 1915 is the lecture of Albert Einstein. That's the general relativity. But the formalism was created by Bernhard Riemann on 10th of June, 1854. And that's one of the most important dates in mathematics. So these two contribute to general relativity. Without the formalism, Einstein wouldn't have written his famous equations. And the other is quantum mechanics, which is 2526. Actually, the quantum idea was born by Planck, but actually the beginning is the 1905, again, Albert Einstein with the notion of Lichtquanta. So the equations, the two most beautiful equations that we have in physics are the Einstein equations, curvature plus a cosmological constant is equal to energy momentum tensor, and the other is the Schrödinger equation in quantum mechanics. And from it, of course, the quantum field theory and all what we know about particle physics. What is an amazing fact that after 100 years of enormous effort of thousands of people, these two equations still do not talk to each other. So quantization of gravity, that was the usual road at the Planck scale, 10 to the 18 GeV. It was canonical quantization to start with, string theory. I spent 17 years on string theory. Loop quantum gravity, my most cited paper is in loop quantum gravity, etc. They did not lead to a unified theory that reproduces what we know at low energies. The standard model is a model of particle physics that has no deviations at all until now. And there is general relativity, which is also extremely well tested, but they do not see each other. So all of them are extremely well tested. The standard model in the part of electrodynamics, it's tested up to 14 digits, and all of them agree between theory and experiment. And general relativity is tested in slightly weaker gravitational fields, but there is no deviation either. So this lack of success of merging the two theories suggests that probably both gravity and quantum mechanics should be modified. That's probably the outcome. One of the arguments is that the measurement, which is this mysterious quantum to classical transition, or usually called objective reduction, is treated in quantum mechanics still as an external intervention. We really don't know why it happens. I would like to emphasize that decoherence explains the measurement only when we have both a quantum and a classical system. If everything is quantum, decoherence does not explain the measurement. Measurement is external to quantum mechanics. So that's the idea that Roger suggested, that gravity can help at least to formulate the criteria when the measurement actually takes place. So in the Einstein general relativity, let's recall that the bodies move along the shortest path. That's what we heard about that in Paul's talk. But it is in curved space-time. They are so-called geodesics. So, for example, the parabola of a stone, when we throw it up, or the motion of the moon around the Earth, or the weightlessness on the space station, they are not caused by gravitational attraction of the Earth, as in Newtonian gravity, but by curvature of space-time. All of them, the stone, the moon, and the space station, move along their shortest paths. So it is not an attraction of the Earth, but the change in the space-time. I would like to emphasize, we will see examples of that in general relativity, there can be infinite differences of time and space measurements by different observers. I would like to emphasize this because we will see examples later on. Conceptually, nothing is left of the Newtonian gravity, except, of course, the equations for in the weak gravitational field. So now black holes. The origins of black holes are more than 200 years old. John Mitchell in 1784 with a very wrong estimate, but independently Simon Laplace in 1796 with the proof 1799, they noticed that if a star's radius was several hundred times the sun's radius and had the Earth density, then the star would not be visible. That was the statement explicitly given in the paper of Simon Laplace. The origin of that was, as we now know, both were wrong in using Newtonian gravity. That shouldn't be used when we go to velocities close to c. So that was the argument of Laplace, that the kinetic energy should be equal to the potential energy. Therefore, if that's the speed with which we have to throw the object to go away from the Earth indefinitely, when we plug in v equal to c, we see that's the r. And that's the r that Simon Laplace has obtained to get this several hundred times the sun's radius. But we now know that the resulting equation giving this 2gm over c squared is accidentally correct, completely accidentally, because neither Newtonian gravity should be used nor non-relativistic equation for the energy. And the interpretation in Einstein GR is completely different. So that is accidental that it works that way. It is funny to note, however, that in the Andromeda galaxy, there is a black hole in the center, that's roughly between 100 and 200 million solar masses, that approximately satisfies the assumption of Laplace, which is this. But it is not a star, of course, it's a black hole. So we heard in the Paul's lecture that there is a notion of metric, which says how we should measure real time, actual physical time, and how we should measure actual physical distance, and that it can change from point to point. That's the very famous Schwarzschild metric, which was obtained 1 month after the Einstein lecture in November 1915. This is actually amazing, since Einstein predicted that his equations that we have seen earlier will never be solved exactly. And after a month, he got a letter for Karl Schwarzschild. And actually this solution gives gravity around us. Gravity around us on the Earth is described by the solution. So this parabola, moon, or a space station are given by this equation. We see that for r going to infinity, this goes to -1, this goes to 1, and we recover the metric, which is in special theory of relativity that we have seen in Paul's lecture. So that is Pythagorean theorem with the minus sign. That's why it pays off to be fastly moving to get younger at the end. That's because of this minus sign. The metric has a problem, as we see here. For r equal to 2gm over c squared, it is the same equation that we have seen before, but now has a completely different meaning, because we have 0 here and infinity here. So that's a problem with this measurement of time that freezes there, and the measurement of distances that go to infinity here. So this is the famous Schwarzschild radius. For the Earth, we have that this number is roughly 9 millimeters. So since we are 6,000 kilometers from RS, this is very, very weak. The gravitational field is very weak. For the Sun is 3 kilometers. Again, the radius of the Sun is 600,000 kilometers. So these effects are very small. But for the black hole in the center of our galaxy, for which the Nobel Prize was awarded last year for Reinhard Genzel and Andrea Gass, this is 12 million kilometers. So it's not such a small object anymore. So from the Schwarzschild solution, if we neglect higher order corrections in 1 over the speed of light, we can derive laws of Newtonian gravity. So that's the connection, but the conceptual ideas behind Einstein relativity and Newtonian gravity are completely different. But full solution is necessary, of course, to describe black holes, for example, or explain the difference of times between us and the GPS satellites. We all very well know that we check the Einstein theory by using the GPS devices. Approaching RS takes finite time for the observer falling into the black hole. So when someone falls, it will take a finite amount of proper time, but infinite time for someone observing from the outside. And that's again the infinite difference in time measurement for different observers. And that's an example that we have talked earlier. So r equal to 0, it is a true singularity because it is the curvature goes to infinity there. Now, before 1964, black holes were treated as a mathematical curiosity, because there was even a proof, as it turned out wrong, that to create a black hole, to collapse into a black hole, full, absolutely mathematically precise spherical symmetry is needed. And now, as we now know, there was a paper of Roger in 1965 with the sentence that deviations from spherical symmetry cannot prevent space-time singularities from arising. So this sentence is worth the Nobel Prize. The proof is given there with the famous drawing of Roger himself. So that was the very, very important paper that has proven that people started to believe that black holes can be there if the mathematical spherical symmetry is not needed. Even if there is some deviation from spherical symmetry, under some conditions, the black hole will form. So that's first part, because we will use the black holes later on. Now the Penrose diagrams. The Penrose diagrams, let's first show the famous drawing that we can project the infinite line into a finite interval, that the stereographic projection. We have the angle phi, so minus infinity is when we point, with this here, so that's phi equal to minus pi half, the plus infinity when we touch this circle and we go there. So the infinite line can be projected into a finite interval, and that's what is an essence of Penrose diagram. So Penrose diagram, now we talk about our universe. I would like to emphasize that we assume that the cosmological constant is positive. The picture will be completely different, as we will see in a minute, if the cosmological constant was vanishing. That would be completely different picture. So the metric again, if the universe is flat spatially and homogeneous and isotropic, can be written in this form. And actually, the Penrose diagram is compressing the infinite time into finite interval, that is time. This direction is time, into finite interval, very similar to what we have seen on the circle. And the infinite or finite or toroidal space is depicted here. But we do it in such a way so that the photon moves along the lines that are inclined by 45 degrees. So we compress space and time, keeping this line inclined 45 degrees. So that's very important. So, for example, something moving with smaller velocity will go like that. But nothing can go faster than light. So all trajectories will be within this cone. There are three lines here depicted: BB, which is Big Bang, LS, which is last scattering, and FE, which is future end. I will describe them in a minute. Here I have given the values for this A of eta. So at the beginning, it is very small because here is eta equal to 0. Here is eta equal to eta infinity. So A of eta is extremely small, which means that the distances are very small. But I would like to emphasize that the Big Bang is not an explosion of a grenade. It is even here very, very close to 0. This can be infinite. So the distances are very small, but the universe does not expand into something. It expands by itself. So that's very important to understand Big Bang, not as an explosion into an empty space. There is no empty space here at all. So the most amazing fact about the universe is that it is expanding. It was first, in a sense, shown by Georges Lemaitre in 1927, before Hubble, and only later Hubble has proven this with his telescope in 1928, with his famous linear law. BB is the Big Bang. It's the initial singularity where distances go to 0. We have seen it before, and temperature goes to infinity. It is necessary in classical general relativity according to the Penrose-Hawking singularity theorem. So such a point is necessary if we follow fully the general relativity. LS is the last scattering. I will talk about this in a minute. It is the origin of the cosmic microwave background, CMB. That is a very important concept, so I will discuss it in a minute. And FE is the future end, when the cosmic time goes to infinity. As you have seen, the conformal time stops at some finite value. So it is infinitely distant for massive particles. So we would have to wait infinite amount of time to reach the upper end of this Penrose diagram. But it is infinitely close for massless particles. Photons and gravitational waves do not feel time. So if we look at the night sky at Andromeda, for us, the time of emission and the time of absorption by our retina is 2.5 million years, while for a photon, it is 0, exactly 0. So it does not distinguish emission from absorption. So photons do not feel time. Last scattering, this time was roughly 380,000 years. after the Big Bang, when plasma, which consisted then of electrons plus protons plus helium nuclei, I would like to emphasize that the universe was extremely simple then. There was only these plus decoupled neutrinos. When it converts, the temperature goes down, and at some point, the plasma converts into neutral hydrogen and helium atoms. And then it is the point in time when the universe starts to be transparent. Plasma is very opaque for photons, while the neutral hydrogen and helium atoms are, the universe is transparent. And that's the origin of cosmic microwave background that travels to us for 14 billion years, almost without any deflection. So it's an absolutely incredibly precise photograph of the universe when it was 380,000 years old. So the temperature was 3000 Kelvin then, but the universe expanded 1,100 times from this time to our 14 billion years. Therefore, the temperature dropped to 2.73 Kelvin now. So it was red then, now it is microwave. CMB is almost homogeneous when we look at different directions of the sky, but there are extremely tiny, around 10 to the minus 5 Kelvin fluctuations when looking at different directions on the sky. So it is almost perfect microwave oven, except that there are extremely small fluctuations looking at different directions. So since these fluctuations are very important, satellites COBE, first COBE, then WMAP, then Planck, recently Planck, were designed to measure these fluctuations. They have to be measured from the outer space because our atmosphere produces too much noise in the microwaves. And that's an extremely rich source of information about the global properties of our universe, since these photons have traveled for 14 billion years. And then measuring them gives an enormous amount of information about the early universe and about the universe as a whole. So let's write again the Penrose diagram of our universe, again for lambda bigger than 0. So this is Big Bang plus scattering. This is us. And now this is not in scale because you see that it should be 1%. Plus scattering should be 1% of this interval. This is 10 to the 16, this is 10 to the 18. But this is in scale. We are in 3/4 of the distance to the future end on the conformal diagram. So those are the numbers. I would like to emphasize here what is very important, that even if we lived to the end of our time, we will not see the whole universe. That would be the portion of the universe that we will see. But for example, this point that is now parallel to us will never be seen. So in the universe with the positive cosmological constant, we see only a small part of the universe, maybe infinitely small part of the universe, we don't know, but that's the only thing that is available to us for observations. All the rest is unobservable and will remain unobservable, except if CCC is correct, that we'll discuss this later on. So that is very important. And that is us. So for example, first star in our galaxy was 300 million years, it is roughly here. Our galaxy was formed roughly 11 billion years ago, that is here. That is the formation of Earth here. And whatever, I don't know, the Jurassic eruption or carbon product or whatever is within this bubble. Everything what we consider as a known history is in this bubble. Okay, so now let's compare it to the universe if lambda was vanishing. The Penrose diagram is completely different. It is a triangle. So that means, first of all, that if we live to the end, we will see the whole universe. That all will be seen. Now, the second statement is that this point is very singular in distinction to the previous rectangle. This point is very, very singular. Second, I would like also to point out that without inflation, the last scattering is here. That's the line of last scattering. So when looking backwards, this point is when we look in one direction on the sky, and this point when we look on the opposite direction on the sky. But we see that they were never in causal contact, because even from the Big Bang, that's the causal contact of that point, and that's the causal contact of this point. So that's why the inflation was, in a sense, invented, because it pushes this line up, so that when we look back, we look at this point, we look at this point in one direction and this point in the other, and they were in causal contact before. That's why the temperature on one side is identical to the temperature to the other side. But if we live long enough, we will see that the one direction should be different from the other, but that will take another 100 billion years or so. So the difference between lambda bigger than 0 and lambda equal to 0 is fundamental. And actually lambda bigger than 0 is absolutely necessary for CCC. So let's go back to our universe with the cosmological constant bigger than 0, and imagine that we have switched on a torch in one direction and the other. So for us, this distance is infinite in time, but for a massless particles, it reaches it in 0 time. So that's very important, that this upper boundary is reached in 0 time. And that's what Paul Todd and Roger Penrose, they said, okay, if this boundary is not very singular, and this boundary is not singular, very singular either, why not glue together above another rectangle and below another rectangle? So let's think what it means. It means that if a photon could reach to the other eon, they are called eons, then we would go to the other universe in a sense. The question is whether we can cross this line, or this line, and if we can prove that there was a previous eon. So the whole idea of the papers that I will describe in a minute is to see whether there are traces of the previous eon on the last scattering surface, on the map of the Planck or W map or COBE. So that's the idea. This crossover was discussed by Paul a little. So that's also the Weil tensor is either finite or even 0, which in a sense resets the gravitational entropy from one eon to the other. The other statement is, if this eon is similar to us, here we have a positive cosmological constant, so the inflation happens here. We don't need an inflation here to push the last scattering, because this point and this point were in causal contact in the previous eon. So we don't need inflation to explain the homogeneity and isotropy and the horizon problem of the standard cosmology, because they were in causal contact. So the CCC, so cyclic conformal cosmology, we assume that the conformal transformation is at the crossover that Paul was talking about. It is possible since Maxwell equations and linear Einstein equations are conformally invariant in 4 dimensions. Therefore, we assume that we live in 4 dimensions, 1 time and 3 spatial dimensions. And therefore, these conformal transformations, that means that for a single photon, it is absolutely irrelevant whether it goes through a large dilute universe or whether we compress it by zillion times and it moves in a very compressed universe with distances and times much smaller. That's just a fact about the Maxwell equations, which is not just a fact of life, but it is maybe hints into something, points into something. So before the crossover, as for example, we will have in our future, there are extremely low energy photons far away from each other. But if we cross and make the conformal transformation, there are extremely high energy photons which are very close to each other. because when we compress also the wavelength of a photon, which makes the very low energy photon extremely high energy photon. And then collisions of these photons may produce massive, highly energetic particles. I would like to emphasize that when we have only photons and gravitational waves, the time does not run, because they are not good clocks, because there is no ticking of time, neither for photons nor for gravitational waves. So once we have only massless particles, the notion of time freezes. It loses its sense. So these collisions at the other end of the crossover produce massive particles, and the time starts to run again. That's the Big Bang of the next eon. The inflation is not needed, as I said, to explain the homogeneity and isotropy, because inflation, the exponential expansion, happens now. We are now in the inflation era from that point of view. And our goal, first with my colleagues, then with Roger, was to convince ourselves to start with that there was a previous eon, there are traces of the previous eon, and that whether it was or wasn't in global features similar to ours. That was our assumption. Now, collisions of black holes. We know that the black holes collide. We have seen these beautiful pictures of gravitational waves produced by such a collision, measured by LIGO and now Virgo. These collisions take place around our present time, slightly earlier or later. So we were looking for the rings of diameter bigger than 8 degrees on the CMB, caused by the gravitational waves from collisions of extremely massive holes in the previous eon. Such large ring cannot be created by any causal process within our eon. So that's the Penrose diagram. That's us. That's the last scattering. We are looking backwards. And imagine that here, somewhere here, there was a collision of huge black holes in the previous eon. So they produce gravitational waves that go along 45 degrees, as always, and they hit the last scattering surface. So what would we see actually with this picture? So let's add, that's in one dimension. We should add 2 dimensions to this to actually reproduce what we see. So there is a picture. So that's let's add 1 dimension. So we have the past light cone, our past light cone, and this is the collision of black holes that produce the gravitational waves. We see that the cross section is just, these 2 points are the cross section at the last scattering. This is last scattering surface, this is the collision, this is us. But we should add yet another dimension because we live in 3 dimensions. So this is a cross section of 2 spheres, actually. And cross section of 2 spheres is a ring. So that's why I'm talking here about the rings, that we are looking for rings, and the diameter should be bigger than 8 degrees, because 8 degrees is the diameter of something that was created at the Big Bang of our eon. If the diameter is bigger, then such large rings cannot be created by any causal process. So it is a kind of proof that such a ring was created before our Big Bang, so in the previous eon. So that's the idea. Of course, when it happens, when the collision happens here, we have something going away from us, which means redshifted. If it happened here, there would be something of similar diameter, but would be blue shifted. It would go towards us. If something happened here, we would not see it at all, because none of it would be visible. So that's the idea of looking for rings that are remnants of the collisions of huge black holes in the previous eon. So that's the rings that we have seen. About the statistical significance, I will tell something at the end. So those are 2 papers that we have published on WMAP and on Planck. They were actually at the same position in WMAP and the Planck, at least those most significant ones who are in the same position. Now, the second idea was to look for evaporation of black holes. Namely, Stephen Hawking has shown in 1974 that black holes are not black. They can emit radiation. They have their own intrinsic temperature. But the temperature of black holes is extremely tiny. For a black hole of the sun's mass, so I would say that's something of the radius of 3 kilometers, so it's not a big black hole, it is around 10 to the minus 7 Kelvin. So it is 1/10 of a microkelvin. For larger, it is even smaller. On the other hand, it takes, because the temperature is so small, we know that the rate is proportional to 4th power of the temperature, it takes a very long time for a black hole to evaporate. For a black hole of the sun's mass, it is around 10 to the 67 years. So it is a really long time. For larger, it is even longer. So it is an extremely slow process for us. However, if we write it, if we draw it on the Penrose diagram, the whole process of evaporation that starts in, let's say, 10 billion years and ends in 10 to the 67 years, the whole process is within the future end borderline. It is hidden there. So it is a point-like injection of energy to the next eon. If we write such a Penrose diagram, here there is evaporation from the previous eon. And from the previous eon, it is hidden in this blob. Everything, this 10 to the 67 years, is within this blob. Therefore, from the point of view of us in the next eon, it is a point-like injection of the whole energy of the black hole into this cone, let's say future cone. I have not used the light rays only because it can produce also massive particles. Massive particles do not propagate with the velocity of light, so the whole triangle is filled. Therefore, what should we see? We should see a disk, not a ring, but a disk, because cross-section, as before, of this with our past light cone would be a disk, that a cross-section of a sphere with a ball. So it is a disk. Therefore, that's what we looked for with Roger and two colleagues. And that's the paper that appeared last year. And this is in galactic coordinates. To look for these circles, for these disks, we have to cut out the galactic belt because there are too many stars that produce themselves the microwave background. So, but the Planck people have produced all the masks necessary to remove bright stars and so on and so forth. And those are the positions that we have found for some inner radius 0.01, that's in radians, of course. And this is 0.03. So that is the in a sense the plot of what we think are remnants of the collisions of black holes in the previous universe that we could have seen within our, because if something happened here or there, here or there, we wouldn't see it on the last scattering surface. Only if something happened here or here or here, that we could see it on the last scattering surface. Okay, so statistical significance, just a few words about this. Unfortunately, we have only one map of the CMB. My background, I'm a particle physicist, so I'm used that if you have some doubts about some result, you add another billion Swiss francs and you make another billion collisions, and then you can make your sigma significance better. But it's not the case here. We have only one map of the CMB. We have created, therefore, 10,000 so-called artificial maps. So they have the same power spectrum as the real map, but they are statistically generated. There, we know that there are no any superimposed patterns of those maps. But of course, statistically generated map can have a disk. But what are these disks? Actually, what we look for is something. Let's go back to this. We look for something. This is an injection of energy that is just then by diffusion goes away from this point. but we look for something that is hotter in the center and colder when we go radially outwards. So we look for disks which have negative thermal gradient. So therefore, that's what we look for. And we compare it with actual disks that can be statistically generated, which have the reverse, which are colder inside and hotter outside. They are not predicted by the theory. Only hotter inside and colder outside are the prediction of the theory. So that's what we are looking for. So we have created a cumulative distribution function for this of the radial temperature gradients for all artificial maps, or for all 10,000 artificial maps and for the real map. We have used a measure of the difference between these cumulative distribution functions with zooming in on the extremal right or left values. We are looking for the disks that stand out. We have used something that I proposed 10 years ago, which zooms in on the extremal right or left values. It is much better suited to our problem than, for example, Kolmogorov-Smirnov test, which also compares, but it compares mostly the average value, but does not zoom in on the extremal value. So that it's a very, very useful tool. And what turns out is that only one artificial map out of 10,000 had more pronounced negative gradient disks, so hotter inside and colder outside, than the real one, which we claim it's 0.01% roughly probability that they are purely random. While if we looked on the other side of the positive gradient, roughly half of the artificial maps outperformed the real map with positive gradient disk, which seems to be purely random. So there's a huge difference when looking for disks hotter inside and colder outside than the other way around. And those are predicted by CCC and those are not. So summary, there are two crucial advantages of CCC. There's naturally low gravitational entropy by the either finite or vanishing Weyl tensor at the beginning, and there is no need for ad hoc assumptions about inflation. The second, it is falsifiable by observations in contradistinction to multiverse, which is not falsifiable. So it does not belong to physics in my taste, but let's not go that far. There are still points to be cleared. For example, amplitude of fluctuations to explain this 10 to the minus 5, and the spectral index, which is claimed to be the biggest victory of inflation to predict 0.96 under special assumptions. CCC is a very attractive, although citing Roger, outrageous alternative to the standard cosmological scenario. And as we say, there seem to be traces of the previous eons which would point to that it is also not only attractive, but maybe realizable or realized in reality. Time will tell. Best birthday wishes, Roger. Thank you.
Well, thank you very much for that talk. An awful lot of information there. And I hope people will keep looking for signals. And if they have another explanation, which I haven't seen yet, for the observations that are in that paper of ours, I would be interested to see it. Thank you very much.
Thank you.
I guess the final talk is by Vahe Gurzadyan.
Yes.
And he was the person who first really looked for signals. I remember giving talks on CCC for many years. I think I originated it sometime like 15 years ago or more, I can't remember now. And I used to give talks with the feeling that nobody will ever disprove it. And so I can go on talking forever on this topic. And then I did wonder about the collisions between supermassive black holes. And it needed Vahe to look in the right way to see that we actually find signals of this sort. And I hope he will describe these things to us in this talk now. Thank you very much.
Thank you, Roger. You see my slide, yes?
And I see the title slide. That's what you mean.
Well, yes. So it's a great pleasure to have the possibility to speak today on this memorable event honoring Roger. I'll speak about the CCC, about the works we did together, also about the cosmological constant in the context of CCC, and of course about the observations in the context again of CCC. So let me I'd like to start from the snapshot of Nobel lecture by Roger, where it is clearly shown the diagram how the observational information can be passed to our EM from the previous one. So Meissner already described the scheme of the appearance of the concentric circles, the rings. So the point is that when we observe now from above, we can detect the sequence, the result of the sequence of the merging of the black holes in the previous eon, assuming that the previous eon has the more or less similar structure of the clusters of the galaxies as we have now in our universe, namely the black holes of the massive black holes in the centers of the galaxy by time will merge in the clusters of galaxies, and this sequence will produce concentric rings. And the novelty which we discussed and we started to proceed together with Roger at the time was that to look not the perturbations of the absolute temperature of the CMB, but to look on the concentric rings of the low variance. So this is the difference from the studies which were made before by that time. So it was about 10 years ago. Therefore, it is a principal point because low variance appears the consequence of the observable events which could happen in the last eon, namely the merging and the concentric rings. So a superposition of those rings can produce what I said here. And so we started to look. But before going ahead on that, I'll speak about the cosmological constant. Because conformal cyclic cosmology of Roger has two essential points. One is the second law of thermodynamics, and the second is the positivity of the cosmological constant. Cosmological constant in two papers of Einstein of 17 is a pioneering paper on cosmology, and the second one, shorter paper of 1918. He called in both papers lambda as universal constant. So I discussed the possibility that the cosmological constant is a second constant of gravity along the Newton's constant of G. Then, if one considers the cosmological constant as the fourth physical constant, along with C, H, and G, then we can come to some predictions regarding CCC, in the CCC context. Namely, that the rescaling of the physical constants is possible in the next eon with respect to the previous one. Let me start from quoting Maxwell regarding the nature of the fundamental constants and fundamental properties. Namely, he spoke about that the time, mass, etc. should be absolutely permanent if they depend on certain properties, fundamental properties. So it was essential statement, and the issue of the units and constants are of course very long durating discussion, and namely regarding the starting the discussion of this of the units, natural units, starting from the Planck units, when Planck in 1900 introducing the new constant h, he concluded that so the phrase here you can see from his paper that these constants retain their meaning for all time and for all cultures. So the issue of the fundamental constants and units are being discussed also now. For example, in early 2000s, there was debates, long, quite active debates involving Veneziano, Lev Okun, Dav, whether the units have to be dimensional or dimensionless, the constants, physical constants, whether they have to be dimensional or dimensionless. So in this context, the Planck units, the Planck length, Planck temperature, and Planck and the mass, which are they are composed from H, C, and G, from the three constants. These three constants, they have no, they don't allow appearance of a dimensional-less combination, dimensionless combination. So this is an essential point which I want to stress. Then, when lambda is considered as the fourth fundamental constant, then a drastic change of the situation it happens. Namely, we come to a combination of a dimensionless combination, which was not possible having the three previous constants. And this is the paper we did with my colleague Arman Stepanyan, where we discussed the consequences of the lambda being considered as fundamental constant. So the dimensionless combination of these four constants, C, G, H, and also of lambda, can be written in this way when for given A, namely when A is 1, and also with some coefficient 3 pi, this coincides with the famous Bekenstein bound. Bekenstein bound is the limiting entropy or information regarding a physical system independent of its nature. It can be a gravitating system, whatever. So it is quite universal. So this combination corresponds to or includes the Bekenstein bound particularly. Also, it includes the so-called the de Sitter event horizon introduced by Gibbons and Hawking in '77. Also, so this is namely this combination has or may have some deep background. But how the lambda can be considered as a physical constant, which can be the motivation. So here I go back to Newton, where he, in essential principle, which he formulated in his Principia, namely the gravity of the sphere is equivalent to the gravity of the point. Point mass and the sphere with a mass located in its center, and of the point mass of that mass will be the same. So there are more, I read that some historians consider one of the reasons that Newton delayed the publication or release of his law of gravity, universal gravity law, that he was delaying with the proof of this statement. But if one consider the general function which satisfies this principle, then we have two terms for the force. One is the first, the classical Newtonian force, but there is also the second term. So, and this note I published in journal, British journal Observatory, as a generalization of the Macquarrie-Milne Newtonian cosmological scheme. Now, in this case, together with the cosmological term, because in classical textbooks on gravity, for example, Meissner, Thorne, Wheeler, etc., it's written Macquarrie-Milne, of course, is mentioned, but stating that it has no any relation to the cosmological constant. While here, cosmological constant can be introduced as a second term in the force, in the Newtonian force. So here, this point can be discussed in more careful way, what we did with my colleague Stepanyan, as I mentioned, that the first constant C1 is corresponding to the first constant of gravity G, Newton's constant, while the second can be corresponding to the lambda, to the cosmological constant. So in this case, we have to find out that the stabilizer of the geometries and the group symmetries for each case, for the Newtonian case and for the Lorentzian case. So depending on the sign of lambda, we know that there are three these possibilities and corresponding isometry groups. And also, of course, they have their they correspond each of their curvature. Then the Lorentz group O13 is the stabilizer subgroup of the isometry group. It means that at each point one has exact Lorentz symmetry. So here in each case one can see the symmetry groups, and in the non-relativistic limit also similarly as shown below. So the weak field limit of GR, namely in the Newtonian combination, but with extended second term, corresponds to the cosmological term in the Einstein equations. So one can look also the dimensional case, higher dimensional case, and we can see we can generalize for that case the Poisson equation and find out the corresponding potentials and the Gauss law and also Einstein's constant. And from here we can see that while Newtonian gravitational constant is dimensional dependent and matter coupled, here you see G is with rho. The cosmological constant is neither dimension dependent nor matter coupled. So in this context, in this sense, cosmological constant can be considered even more constant, physical constant, than the Newtonian constant in this context, as I mentioned. So as I said, I am motivating, I am trying to bring background why cosmological constant can be considered as a universal physical constant. Again, the term universal was used by Einstein in his two original papers. So if we use this weak field extension of the GR, of general relativity, namely the Newtonian term also with the cosmological term, then this can be used to describe the dynamics of the galaxies, groups, and even this can make possible to solve the Hubble tension. I'm mentioning this because each statement, word here is we have published in a separate paper, particularly about Hubble tension, how it works and enables to solve the Hubble tension. I remind that Hubble tension is the discrepancy between the so-called global value of the Hubble constant, namely the value which follows from the cosmic microwave background measurements of Planck satellite, the recent data of 2018, and of the local measurements using the distant descriptors of the galaxies, so Cepheids and some other descriptors. So the second part of the studies are performed by Nobel laureate Adam Riess and his group, and a bunch of papers are published, and the Hubble tension is considered as a possible problem for fundamental physics. Of course, there are a lot of things still to be understood regarding the systematics of each methodics of each approach of the analyzing of the data. So now coming to the Penrose conformal cyclic cosmology. And so the sequence of the ions already discussed today is how it can be associated, what I said regarding the consideration of the cosmological constant as physical constant. So in this case, we have the, as I said, the combination, the dimensional combination here, and which for the given n and m can be considered as a dimensional qualitative descriptor to describe the evolution of the universe, the dynamics of the universe, starting from the initial Planck era up to the final de Sitter. And this combination as a dimensionless combination, of course, will remain invariant under conformal transformation. Then one can see that the following possibility will appear, namely, the c can be rescaled, c, the velocity of light, h, g, so all they can be rescaled from one eon to another, to the next one, unless this combination, satisfying this combination, the combination of these coefficients, one can see. Of course, there is some difference in the role of lambda and other constants. Namely, the lambda is absent in the Planck era scales. And so by fixing the lambda's value, the values of other constants will be fixed at each eon. So this is the, and of course, this rescaling has to satisfy some group symmetry, which is written below. So this is the statement. I wanted to conclude the question which I started to discuss initially, namely, if one considers lambda, positive lambda, as a constant, fundamental constant, along with the three other constants, physical constants, then one can arrive this conclusion that the constants can be rescaled from one eon to another, satisfying some condition. So this is the one of the points I wanted to discuss. The next one is the role of the cosmological constant or dark energy on the time arrow. So in this paper with my colleague Armen Alaverdian, we showed that the lambda can influence the appearance of the time arrow. Particularly, lambda can induce hyperbolicity of motion with the consequences of the time asymmetry, dynamical entropy production, etc. And so if we remind the definitions of different time arrows, the thermodynamical, increase of the entropy, electrodynamical, retarded potential, cosmological, expansion of the universe, quantum mechanical. So these are the also some others can be defined, but of course it is known, including also Roger has discussed this in his well-known papers, that not all of these arrows are independent. So they can be reduced to possibly to two arrows, thermodynamical and cosmological ones, the rest ones. And then, well, if one considers the Hamiltonian of a system, for a system and the bat and the interaction, then the thermodynamical time arrow of the system can arise in the system due to the limited observability of the bat of the this second term in the Hamiltonian. So in this case, the cosmological constant, the dark energy, takes the role of the bat. So this is the bat, which is interacting with the physical systems we observe, and for whom we see the cosmological arrow of or thermodynamical arrow. So this can be, in this description, can be described as a consequence of with the interaction of with the bat. Bat, again, in this case, can be the dark energy with limited observability. And because of that, we have the emerging of the arrow, thermodynamical arrow. Now, I want to move to the next point about the CCC and the Fermi paradox, including discussion of the observational consequences, what we did in our study. So this is the paper of 2016. When we started in 2010 to discuss the observability and how to try to detect the consequences of the CCC, I mentioned about the low variance rings. At that time, the data were available from boomerang experiment, balloon experiment in the Antarctica, of a piece of sky. And then came WMAP and Planck data. So we published the paper in 2010, 2013, and 2016. Including all the peered observational data of that time. So what we saw, that the half-degree rings within some interval with some dips, when the galactic disk masked, so it is more or less standard mask used by all those studying CMB, then we see that up to the 16 degrees, which is compatible to the theory predicted by so this American group and also Paul Todd in 2012, we saw some sets of concentric rings. So the parameters here are mentioned in these tables of the WMAP of the 94 gigahertz and Planck data of which appeared later of 70 gigahertz, and also EnSight 10 to 2024. So it is the pixelization, so resolution, let's say. So and we see the number of those sets. Below you can see with 3 and then 4, more than 4 circles in the set. So here above is WMAP 94, below is 70 gigahertz. Both are when the number of cycles are 3 and more. Then here I mentioned that a Canadian group repeated precisely, or more or less precisely, the algorithm of our search of this signal, of these structures. And they stated that they were able to reproduce our analysis, and they confirmed the existence of the appeared structures. So I want to say that there is no doubt that what we did was absolutely correct and absolutely valid. So this group just checked repeated our analysis and concluded that those structures, they confirmed the existence of the structures we saw. However, the structures have quite essential properties about what they say nothing, but we consider those properties are quite important. Namely, here you see the same plots what I showed before, but for the 4 and more circles in the set. And we see that these sets are quite clumpy. They are not distributed homogeneously over the sky, but they are clustered, they are clumpy over the sky. So this is striking evidence that something inhomogeneous, some structure, signal exists at such kind of analysis. Then, if we consider the mean temperature of these sets and assign some color, namely here from the blue, from the cold to the red, to the hotter temperatures assigned to those sets, and if we show the centers of the sets, as it is shown in these two maps, so above are 3, more than 3, I mean 3 and more circles in the sets, and below are 4 and more. What we see, besides the clumpiness, so a striking inhomogeneity of these centers, also we see the segregation in the color. Namely, some part is red, is so hotter, and some is greenish or bluish, etc. So in the context of CCC, this color have to indicate the distance, this distance in time. So how back in time, in previous eon, this particular merging has occurred. So this is an essential information, additional information, besides the concentricness of these circles. So again, these are things which are these two properties, namely the clumpiness of their centers, which are quite striking, clearly seen. And the second is the color segregation, that's a temperature segregation, which is again in context of CCC is the indication of the distance in time of the events. So here for comparison, we have simulated the map with the same sigma and median of the Planck 70 gigahertz maps. So we took from the real observational data, the sigma, etc., and simulated the map. In the simulated map, we see Gaussian map, of course. We see that the distribution is completely different what we saw in the above. We see in the above plot. So this is the indication that some non-Gaussian signal is seen in the case of such an analysis of the CMB data. Now, coming to the second part of our title in the paper which Roger I showed a few minutes ago, regarding the Fermi paradox. Some years ago, I published a paper about Fermi paradox, stating the possibility of using the so-called Kolmogorov complexity and predicting what is called information panspermia, namely that bit strings can be quite convenient mode of transmission of intelligence signals rather than some coded signals or coded information, transmission of coded information. So Kolmogorov complexity is the definition is briefly written here, is the length of the program, binary coded of the program, which is enough to recover all some system, completely recover all the information on the given system. So it is quite fundamental some concept used and applied in quite different areas of research, because here it is the length, the complexity, the definition of the complexity, and also because it is it has to be attributed to the Turing machine, also something universal. So this is this approach can be used as I suggested in information panspermia, namely to propagate the bit strings with coded information, and in this way using some one-Neumann automaton network, for example, to propagate the light over the universe, over the galaxy. For example, the time scale can be quite short in comparison to cosmological time, or even 10 to the 26 centimeter can be covered to the during the Hubble time. So in the paper with Roger, we speculated, let's say, that the information from the previous eon can why not, can contain some encoded information about some bit strings with about some intelligence or so. We have some paragraph there. I will not speak about this now, but we have some things there discussed very briefly there. So let me conclude that gravity, if we came from some basics, starting from Newton's principle, etc., and using the generalized function satisfying Newton's principle, etc., then can be defined by two constants. The G, Newton's constant, and the cosmological constant. If so, then one can come to some dimensional independent and matter uncoupled version of the cosmological constant content, and from these four constants, by means of these four constants, one can define some dimensional combination ratio which is invariant to conformal transformation. If so, then the rescaling of physical constants from one eon to another can be possible. Of course, I don't discuss the consequences of this event, because if the fundamental physical constants will be rescaled, some essential differences in the next eon or in the previous eon one can imagine in very, very different way. So because again, physical constants govern in many contexts not only for example the stars but also the life, the structure of the gene, etc. Then this dimensional constant can be used also to define the quantitatively the increase, the discrete the increase of the information in the universe. So the cosmological model can be described as a model of the increase, discrete increase of this combination. Then coming to the low variance concentric circles, I again want to outline the 2 points I mentioned already, the inhomogeneity of the clustering of the concentric circle sets, and the second, not less important, maybe even more, then the mean temperature shows clear segregation. So the difference in the colors, in the temperatures assigned to the centers we see are very different. So these 2 points, both points are quite compatible and find their explanations, natural explanations within CCC. So I want to show this picture with Roger were in ancient city in Ercolano in Italy, and of course a lot of discussions before that, after that, during these many years, and I want to congratulate him with the birthday and wish him more and more inspiring ideas, so what we will happy to discuss and to work on that. Thank you very much.
Well, thank you very much, Vahe. That's fascinating. I think even for people who don't believe a word of CCC, they have to explain, I mean, your very striking non-homogeneity of the points that you find. I mean, somebody's got to explain that. I mean, CCC is telling us something more. It's telling us not just to take CCC seriously, but it's telling us that on this very, very large scale, the universe is not really as homogeneous as people seem to think, which is a striking piece of information, not anticipated by me, I may say, but from your very striking pictures, you can see this highly inhomogeneous pattern of these points. And I've not heard anybody address that issue, even if it's something completely different from CCC. How could you explain that enormous difference from homogeneity? And not just in the location, but as you point out, in the color, which in the CCC would be a question of the distance from us. But whatever the explanation is, it would be outside conventional cosmology as far as I can see it. So thank you very much. I guess it's questions, is it? What does it do at this point?
Yes. First of all, thanks to all the speakers. That was a fantastic session. I'm hoping that Yvette has been monitoring the Q&A. I have been too, but Yvette, are you there? Have you been looking at the Q&A?
Yes,
I'm here. We're going to get you. Okay. Do you want to feed the questions, please?
Yes, sure. So there is a question here. It says, is there a correlation between the locations of the Hawking points and the concentric circles in the CMB? Since they both originate from black hole phenomena, you should expect them in roughly the same positions in the CMB sky.
Yes, well, the thing is, we only catch the Hawking points when they're just where our past light cone hits the crossover surface. So you see a very small proportion of the Hawking points, according to the theory, all over the sky. But if you look for those points and you look for, in Vahe's analysis, those would be colored green, sort of an intermediate color from the red ones and the blue ones would not be where our past light cone hits the crossover surface. So it would only be the green ones. And out of the 6 really convincing points in the analysis that we did, that was published in the monthly notices, I think there were 6, as far as I remember, 6 points which we see convincingly in both the Planck data and the WMAP data. If you take those 6 points as points to be confident about, and then you look to see if they are almost identical with green points in Vahe's analysis, we find 3 of them, 3 out of the 6 pretty well coincide, which is pretty good, I think, because that means we're looking at least a Hawking point which has come about from at least 3 big collisions with other supermassive black holes. I mean, you might miss some for various reasons. I thought 3 out of the 6 is pretty good. So the answer is there is a correspondence. I don't know if Vahe wants to comment on this further.
Well, no, I think you said, you described the situation as it is. Yes, I think so.
Yeah. Yeah, so the answer is we do see it to what more or less the extent we would expect to. I mean, that you don't see it in the red or the green point, the red or the blue points, because that wouldn't register as a Hawking point. You see, to catch the Hawking point, you have to see it just as it crosses over into our eon. If it's inside, you wouldn't see it. If it's outside, you wouldn't see it. You would see it. There's a little bit of play in that. You've got, what is it? The point is 4 degrees.
Yes, that's what I have shown on the Penrose diagram. Yes, it is a very small percentage that we can see with the temperature.
That's right.
That's a different thing we are looking at with temperature.
And also they are greenish. These 3 what Roger mentioned, they are greenish. So
greenish, this is exactly consistent with what you'd expect. Yeah.
Yes.
So I hope it's okay if I add a little bit to that question, which would be, would there be a different signal coming from a different phenomena that you would expect to coincide as well? I remember Roger talking about dark matter decay and so on. So would there be a correlation with such type of signals as well?
I think there's a question. I don't know about the dark matter decay, because that's we haven't got to the point where we can relate observation to theory there. It would be interesting to do so. I mean, there are a lot of potential observations which people haven't looked at yet. We'll have to work on them. But your question was what? That there might be some other. Can you repeat just what you said? Because
yes, because the question was about, the location of the Hawking points and also the circles in the CMB. But I was just asking if there would be another sort of effect that you could expect to also be correlated in the same location.
Well, another thing that I could think of is concentrations of matter. You see, there are some mysterious things in the CMB that people accept. One is the thing called the cold spot, and that could be. You see, in Vahe's picture, you see a very big red region in the sort of just below the central strip, which is eliminated. Below that, you see a very large red spot, which would correspond to a very distant, outside our particle horizon, according to the theory, a very distant, huge collection of galaxies. Now, it may be that, you see, the edge of that, where what they call the cold spot, is roughly on the edge of that region, as far as I can remember. And it might be, it would have to be looked at more carefully, but it might be, you see, you're looking at a depletion of material in our eon because it got attracted to the big red region. And so there's a slightly lower concentration. Maybe that would cause it to be a bit cold. There was another thing which I wondered about, which is the opposite effect. The blue region you see in Vahe's picture up at the top right would correspond to things which are within our particle horizon. So that seems to indicate a great, enormous collection of stuff. And maybe you would see that in some other effect. I was getting quite excited as it might be. You see, these observations of quasars in our eon, you see that would indicate they are found to be quite clumpy. So they're not as uniform as people think. And it might be that they would correlate with the blue region. At a preliminary look at it, it wasn't as exciting as I was hoping. The biggest collection of quasars seems to be just on the edge. But then quasars correspond to a certain time in the evolution of a galaxy, and it would be perhaps a complicated issue to see exactly how to correlate this effect. But that's something you might look for. I mean, I think there are things like that. I think potentially there are quite a lot of effects that we haven't looked for yet, which could be a test of CCC in one way or another.
Okay, so now a very different question, and I think this is one that maybe the different speakers can give their opinions. So there was a question about what's your opinion about the multiverse?
Okay, I'll pass it to other people then.
Me too. I have expressed my opinion.
I also pass.
No, but you can say if you don't like it and why. I mean, it's like a question for
I
the
may say
general
something,
public.
yes, because multiverse, you know, that's an almost natural consequence of string theory, on which I worked for 17 years. So in a sense, I got used to this idea. While since it is not falsifiable, at some point I decided I will quit on looking at that, because it is not physics. I have to present some experiment, even Gedanken experiment, with which I can falsify the birth of new universes all over the place. Since I cannot, since they detach from us in any causal sense, I started to think that it is beyond the physical intuition. I'm a particle physicist. I started as an experimentalist. Now I'm a theoretician for 40 years, but it is beyond the physical intuition I can think of. Something has to be falsifiable.
Just to be confrontational and provocative,
Absolutely.
There are those that say it is possible to detect directly causal imprint from the collision of our universe with another universe. This is work Hieron Pires and Latham Boyle and others, basically circles in the sky, not of the Hawking point variety, but indicative of a bubble collision. That's one state. I'm not saying I back that, but something I've talked about. Done a video about. And then also, the question of what is falsifiable is, again, it's not sacrosanct. It's not given by God that is the criterion of science. So people say there is a testable program, provable pathway through that, is similar to the lack of direct observations of quarks or something like that we are also forbidden, even in principle, from detecting. We can only see secondary interactions. So people say this. Again, I'm not defending it. I'm just saying that I think it's thrown around a lot that this is falsifiable. And by the way, we could have falsified inflation, right? I mean, if we had measured the curvature of the universe and it was different than zero, I think that would have been a big strike against inflation. Now, again, it doesn't mean you can prove that inflation took place. I'm just merely pointing out there are consistencies, and then there are extrapolations to potentially unobservable things, just like the singularities are as well.
Yes, but inflation is a different thing than multiverse. It's not direct, the inflation is falsifiable. It is part of physics. That's absolutely, I do not deny that. Mm-hmm. Because we can check eventually, if we wait 10 billion years or something, we can see whether the inflation ended with 60 e-folds or whatever. And then we will see the difference at the different parts of the universe when we look at. So it is falsifiable. While birth of the new universes that detach causally from us, and we can have no contact whatsoever, that's also different from the collision of the universes. So those are completely different scenarios. So inflation, yes, it is falsifiable. It may be part of physics. absolutely. The collision of the universes, whatever it means, but that means that they are part of the same universe. That's not the multiverse in the usual sense, in the birth of new baby-born universes. That's a different story in a sense, I would say.
Yeah.
Does anyone else wants to comment? Maybe Paul, do you want to comment on it?
Let me just unmute. I don't know enough to have an informed comment, but I do rather share sympathy, obviously, with Roger, who's being very discreet and not saying one thing or another. I'm sympathetic with what Krzysztof says. It doesn't feel like, well, it sounds bizarre and ridiculous, and if as well as being bizarre and ridiculous, you can't test it, surely that's got to be the end.
The advantage of CCC, it's bizarre and ridiculous, but you can test it.
Yeah, it could go down tomorrow.
Yeah, yeah, that's right.
So there's a question here about, let me see if I'm phrasing it correctly, but if you take a singularity and you can expand it and make it coincide with a boundary, there's a question if you could do the opposite and sort of take a boundary and collapse it into a singularity. I mean, I can read it, but that's, I think I actually saw two questions in that direction. So I guess perhaps the question is about, could you have like a universe that the end part goes back into a singularity? I guess it goes in that direction.
I think the more constructive thing, sorry, I'm not muted. I think the more constructive thing is the picture that Roger's given us, that you can blow it up at one end and shrink it at one end, and then you get this nice long stick of bamboo which goes from node to node to node. It's true, you could now take the future boundary and shrink it down, but then why would you want to do that? I mean, you blow up the one at the beginning because it was singular, and now it's been blown up, it's not. And you blow down the one at the end because it was infinite, you know, in other words, pathological in a different way. Now you've made them both, in a certain sense, you've made them both a good deal more tame, and you've got something constructive to work with. You could do more Baroque things and tie them in knots and so forth, but if you want a nice picture of the universe, you do the ones that I was talking about.
I think there is a question which people often ask, is whether the constants of nature could change from eon to eon. And certainly it's worth thinking about. It's a bit of a problem with getting equations which work and these numbers change, and particularly the cosmological constant, as Vahe was talking about. I would say there is a little bit of evidence that they don't change. And one of them was a thing you pointed out about the maximum size of the rings which can come from collisions between supermassive black holes. And it's sort of the size that you see, the biggest size you see, is pretty well consistent with what the theory would tell you is about as big as they could get. So it's sort of not a huge factor, but I mean, I would say something rather indicating a not enormous change, at least in the constants of nature.
Yes, that can be used to constrain.
Yes.
So there's a question here about entropy and the second law of thermodynamics. So it says, the second law of thermodynamics is based on an isolated system. Do we think that the universe follows the second law of thermodynamics and that entropy increases? Is the universe an isolated system?
Am I allowed to answer this one? I mean, yes, I don't quite know what an isolated system is, because you can say take the whole system and then it's isolated because it's the whole lot. And that's what we're doing here. So I don't see anything wrong with talking about the entropy. You have to talk about it in the right way. But the picture I slightly changed my mind in this. So let me give you the version which I think now is right. You see, it was a very strong factor in CCC. And I think perhaps it was Paul, somebody showed the picture of the, I can't remember whether it was Krzysztof, one of you anyway, showed this picture of the the entropy, when you have a gas in a box or something like that, then the gas tends to spread out and be more and more uniform. So the entropy increases corresponding to getting more uniform. Whereas if it's a lot of stars in a huge galactic scale box, it goes the other way. And so you get it more clumpy. And what we see is very uniform, both which says high entropy in the matter, but where does the low entropy come from? Well, it comes from the uniformity in overall, the gravitational uniformity, which says that you've not used up the gravitational degrees of freedom. But then the question is, how does, in CCC, you might say, well, there's a paradox, because if the entropy is going up and up and up, how does that square with the picture presented by CCC? Well, the answer seems to be that the entropy, as it goes up and up, it gets more and more concentrated in black holes. By the Bekenstein-Hawking formula, you see it absolutely swamps everything else. When you get a significant number of black holes, almost all the entropy is in the black holes. Now, whether or not you consider the entropy in the final radiation to carry away, a significant part of the entropy, or is it in the singularity or what have you, it doesn't make much difference, because when you follow into the next eon, all that stuff, whether it's the Hawking radiation or whatever, is concentrated in a single point in the crossover, and that's the Hawking point. But there, it's basically on the other side, you're looking at physics, which is beyond Planck scale physics. So you just wave hands around and say, well, all the degrees of freedom seem to get wiped out, or a good deal of them. And so that's why you can have a consistency, but it's a little bit puzzling. I mean, you see, as the black holes in the remote future collect all the entropy, basically, and then including all their Hawking radiation, which in the crossover to the next eon, that is one point in the crossover surface, and that's the Hawking point. So that who knows what happens to the physics there? You'd have to have a physics which describes what is effectively beyond Planck scale on the other side. So I would just say, well, the information is destroyed, and so the
Actually,
whatever.
that's another question that I was going to move to now, that I guess it's in that direction, because the question is about modulated signals being able to be transmitted across eons via the Hawking points. But I guess the question perhaps is about information being able to go. I guess that's why the interest in the modulated signal, I would guess.
Well, it can get through. I mean, that's part of what Vahe was talking at the end of his talk. The paper we had on the what's called the Fermi paradox. The question is whether you could get some very advanced civilization, say, who are clever enough to send a signal through into the next eon. It's theoretically possible. I mean, you have to require some very stable civilization. I suspect we're not stable enough, and we might do something horrible to ourselves. But amongst all the advanced civilizations, there might be a few which stabilize their civilizations and to a degree where they can actually send signals across. So it's not impossible. I mean, it's wild speculation.
There was a question as well about being able to, transmit something from one eon to another with gravitational waves.
That too, yes, you could do that. Well, that's, you see, in the collisions between, that's what we're saying. In the collisions between supermassive black holes, what you are supposed to be looking at, that's what we claim, is you're looking at the gravitational waves and the effect of them as they come through from one eon to the next. So yes, those signals can get through. I mean,
I would add to the entropy question that there can be some residual entropy stored in photons and gravitational waves that were not inside the black holes. So that can be transmitted from one eon to the other, slowly accumulating in a sense. So there can be some remnant of the second law, but the main, of course, the entropy connected with our black hole in the center of our galaxy has more entropy than all photons taken together in the observable universe. So this vanishes in a sense, but there is some residual thing that can go from one eon to the other. So there can be very slow accumulation of entropy, independent of the gravitational eating of the entropy that we have in black holes.
I think you've mentioned a good problem that somebody has to work on. Just to
Yes.
see.
Yes, and this residual entropy will become the mean of the transfer of information,
Absolutely.
about which was the question.
Yes.
Usually I would expect it to stabilize so that the information in the photons doesn't increase or decrease as you go from eon to eon. But that somebody should look at that. Or could it oscillate? Could it go up and then come back down again? Or all sorts of things are possible. Yes. But
Yes.
You're right. That is another factor which should be looked at in some detail. Yes.
Mm-hmm.
So there's another question. If time does not exist only when photons are there, how do they collide?
So maybe I'll answer because that's my statement. Namely, time exists, but there are no clocks. Because if we have only massless particles, that's the assumption of the CCC, time exists, but there are no clocks, first of all. Second, the photons have very low energy, so they cannot, even if they collide, let's say, we know that in quantum electrodynamics, photons can collide, they cannot produce any massive particle. Therefore, there are no clocks produced. While if we are after the crossover and the energies are extremely large, any collision of photons can produce a pair electron-positron, for example, or a quark-antiquark, and they are massive. So then the time runs as before, but now there are clocks in the universe. So the time does not run in the operational sense and not in the actual sense. Then it runs, but there are no clocks. On the other side, it runs and there are clocks produced by these collisions.
Okay.
I guess, can I just add a little bit there? I guess it's worth saying that's how it comes about that there's an infinite amount of clock time before you get to the future boundary. But because there aren't any clocks, that particular time has gone out of physics.
Yes.
And you've got conformal time, and there's only a finite amount of conformal time until you get to the future boundary. So this is how the conformal rescaling allows you to have a completed infinity. A completed infinity is normally anathema, but you'd have a completed infinity in clock time or proper time or whatever you want to call it. But you haven't got to the end, you've got to the next beginning. So.
Yeah, these questions about time and clocks are really fascinating. Okay, there's a very different type of question here. I'm not very familiar with this, to be honest, but it's asking about Eric Weinstein's theory of geometric unity. So it's asking about a comment on that.
Does somebody know about this theory? Yeah, of this group?
No.
Yeah, that's why I say I'm not familiar with that.
Eric Weinstein, you say?
Yes.
No.
I'm very familiar with it. It would take a long time for me to comment, and I've spoken to Eric a few times about it on my podcast. So people can check out an abbreviated version of his revealing of it on April Fool's Day of this year on Into the Impossible on YouTube if they're interested.
But can you answer the question?
Could you tell us a little bit what it is about?
His theory postulates a massive reimagining of what space-time is. It has less to do with cosmology or big black holes in the Big Bang than kind of revamping the standard model and obtaining a grand unification of particles, forces, and fields with gravity. So it is a quantum gravity theory of everything contender that makes use of extra dimensions, including extra dimensions of time as well as of space, and makes new testable predictions, such as the existence of Schwinger fermions, spin 3/2 particles that are elementary, not composite, that have yet to be observed, but could in principle leave an impact through the Big Bang nucleosynthesis era. So we're working together on certain implications cosmologically, so it could be tested. And so people can stay tuned for that.
But as I remember, there is the margin is smaller and smaller with the LHC results. Yes, because there are many number of dimensions, new particles, but it is less and less the margin of let's say coupling or change of the standard model is very, very limited.
Yeah, so supersymmetry, it has some shades of it. Again, I'm looking at it from the experimental consequences in the BBN epoch, and possibly for Chern-Simons like effects in the electromagnetic sector. No, not commenting on it necessarily as pertains to supersymmetry, but yes, that is true. Things that hold true for ruling out supersymmetry would have some impact on the Bayesian criteria for belief in geometric unity.
I spent many years at CERN, so I'm very personally touched by the results of LHC.
May I ask a question to Krzysztof? When was it I first met you in Warsaw? Were you still working on particle physics?
That was, I think, 2010, I think, roughly, around.
Yes.
Roughly. That was the GR meeting in Warsaw, I think.
Oh, was it that one?
Yes, so that was roughly 2010. No, I'm still working on particle physics with Hermann Nicolai, with Gravitini at the beginning of the universe. We want to explain the giant black holes at the very early universe and so on. So I'm still working on particle physics.
Okay.
But still, yes, it was roughly 2010.
Yeah. Okay.
Yeah.
So Roger, there is a question about you. Are you working on a new book? Somebody's asking.
A question to whom? Sorry.
To you.
I think.
Oh, to me.
Are you working on a new book? That's the question.
Working on it is a quite subtle kind of word there. In a certain sense, two books. But the one which is more seriously being worked on is a book called Eschematics, which I was supposed to have been writing a long time ago. And I've now acquired a co-author, so we might be able to get it finished, because I was unable to put it into any kind of shape. So this is a book which is on the work of the Dutch artist M.C. Escher, and we saw a nice example in Paul's talk. But all sorts of, more than one example, that's right. He showed the picture, the print gallery too. The print gallery and the circle limit, one of them. But you see, there are a lot of, it's very curious because there are a lot of things that Escher did which I never realized when we go through these things. I mean, there's one of his pictures which does a beam splitter. I'd never realized this before. You can see there's a mirror, which is evidently a half silvered or something, and then there's creatures walking up to it, and they get split into two versions. So that illustrates all sorts of things which I'd never realized were depicted in Escher before. But perhaps that's the one that's being talked about. I have an idea for a book, which is another one. I don't know whether it'll make a book. This is on the collapse of the wave function. But these things take time, and I don't know how much time I have to do these things. It should be. So it was the Nobel Prize which killed it off in a certain sense, because I was writing these notes and sending them back to a lot of colleagues, and I thought it was making some progress towards a proper narrative, and then the Nobel Prize came in and stopped work on that thing almost at once. But I hope to get back to it. That's true. So that's two books, if you like. There's another book which ought to be written. I can't see myself doing it, which is the update of the Cycles of Time book. So I wrote this book, which is a description of CCC, but that was before there were any observations. I think I did discuss the possible observations of supermassive black holes colliding and the effects that you would see, but I think it's before any observations. Mm-hmm. So it needs to be redone, maybe with a whole section or a whole new part on all the observations and how the theory has developed since then.
Mm-hmm.
But that should be done somehow. I don't quite see how to do it at the moment. But maybe that needs a co-author too.
Yeah, well, I'm sure people would be happy to do that. So Stuart, I think I pass it to you. I don't know, because you said you also went through some questions, so maybe you picked different ones.
Keep going, please. You're doing a great job. We get a few more minutes at least.
Okay, well, that's why I was passing it on to you, because I'm starting to run out of questions that I sort of understanding. So there's one, I guess, a bit more technical one for Vahe, which is, does your approach require lambda to be strictly larger than 0? And what happens in the case where lambda is going to 0?
Yes, it is essential that lambda is positive. I mentioned when lambda is 0, there are different symmetry groups. So what I discussed is it is essential the lambda to be positive. And in fact, on the consequences also I discussed for CCC is again because it is positive. Because CCC also requires positive lambda.
That's right. Yes, infinity has to be space-like, basically. So it looks.
Yes, yes.
I mean, the Big Bang is, in a certain sense, automatically space-like. And if you're going to match them, you have to have a remote future or a future infinity, which is space-like too.
I have shown the difference between the rectangle and the triangle. It's a huge difference.
Yes, you're right. I'm sorry. It is a huge difference. It's a shame that all the work that lots of people, Bondi and Troutman and Ted Newman and Ray Sachs, the work that we did on gravitational radiation, and it was almost, sort of almost complete theory. And you have to start all over again with a cosmological constant.
Yes.
Because all that depended on infinity being null.
Yes.
And I don't know of any analysis comparable to what was done at that time, which applies to a space-like infinity. I've heard lectures on it, but they don't seem to get to the point, because I haven't seen, anyway, anything that did, where you get lost, and you can define the energy carried away by gravitational waves and things like that, which is important, of course, for LIGO and all that stuff. But that assumes the limit in which you can ignore the cosmological constant. When it's there, I don't know how you measure the energy flux at infinity.
Especially that it is unobservable for Scri plus is observable for any observer who goes to infinity, while Scri plus, whatever it is, the space-like, for lambda bigger than 0 is unobservable. So what to integrate over to get the ADM mass or Trautmann-Bondi mass or whatever?
Yeah, exactly, yes.
Very different.
I haven't seen anything which I find convincing on that.
Yes.
I don't know, Paul, has you answered that question? Paul?
Yeah, I'm just unmuting. Well, you can. I had that article with Laszlo Szabados, which follows your notions of quasi-local mass, but doing it with two spheres that are on space-like scry.
Yes, yes.
And there's a definition that you can give. It's rather complicated, and it isn't totally clear what you can do with it at the end of the day, but it has all kinds of naturalness properties and positivity properties. You can bolt it onto a Witten type positivity argument, and it uses two surface twisters. So it's it does at space-like scry what you've done at null infinity, but you don't get Bondi-Maslov's formulas because you can't. I mean,
but I would have difficulty with that, but I wasn't sure that it was. Yeah, no, I'm interested in what you said. Perhaps you can show me. Yeah,
I mean, I would have thought the way to look at it is that the formulation with a null scry works locally, and the LIGO stuff for these purposes, it's big, but it's still locally, and that's what you say.
That's right. Yes. Yes, I can see you don't need it for LIGO. I mean, they may be a long way off, but they're pretty close from the point of view.
Yes, far away from scry. Yes.
So what is the most important thing now, the next steps for CCC, if there were students interested, postdocs interested, other researchers interested in doing research in this direction? What would you say are the most important questions and the most urgent things to do?
Well, I should think there are a lot of things connected with observation, like magnetic fields. I mean, this was, I think I remember Paul mentioning this to me at one point. You would expect perhaps magnetic fields to cross over and perhaps create a signal that could be seen, well, like what Brian was talking about with bicep 2 and all that. Maybe it's a sort of thing which might contribute to things which could otherwise be thought to be B modes coming from inflation or something. But these would be another possibility for creating, if electromagnetic signals going across. But these would be very, very long wavelength things. So you're looking at just slow changes in the electromagnetic field. So that could, I would have thought there are quite a lot of things to look at. Comparison with the quasar observations would be an interesting thing to do, because that looks very non-uniform too. And can one do calculations? I mean, this is only very recently when I saw these things, but you seem to see the biggest collection of quasars. These people talk about what the large quasar clumpings or something, and then this is the huge large one. And it's very close to Vahe's blue region up at the top right. And according to CCC, there'd be a lot of black holes there. And so therefore a lot of Hawking points, and therefore a lot of mass coming through, which would be more than in other places. So you might expect to see effects in our eon. Now, it's not just an observational thing, it's a theoretical thing. Somebody should really work out. And other things which Krzysztof was trying to get me to, well, I was trying to get him to do it. We were both trying to get each other to do it. Work out exactly what the mass of the Hawking points, the ones we see, so let's say the 6 points, which look pretty convincing because they're both in W and Planck, and they're the strongest ones overall. What is the mass of that supermassive black hole? We'd expect it to be something like a pretty reasonably large cluster of galaxies. But you see, you don't see them all, so it's a selection out of the things you just hit, the past light current hits. But somebody could make an estimate, I suppose, and see how big black holes you would expect to see. And does that correspond to the strength of the Hawking points? That something needs to be done. Likewise, the strength of the signals in Vahe's analysis. How massive are those, assuming that it's correct that those are the collisions between supermassive black holes? How massive were those black holes? I think the information is out there. This needs to be done.
Also, Roger,
Yes.
maybe it could be interesting to see two interpretation of the coloring, segregation of in the colors.
Yes,
the distance in
that's
time.
Right. No, that's a very important factor. And the fact that you see the green ones at these Hawking, at least you see, what was it? Out of the 6, you see, we saw 3, wasn't it? Yes. 3 of the green points, which were, I don't know if there are any of the others. That's a good question. You see points of any other color close to Hawking points? I mean, those green ones were just 1 pixel away or something, weren't they?
Yes, the color.
I would add the flagship of inflation, namely the spectral index.
Oh, the spectral
index within CCC, because that's the flagship of inflation, that the Mukhanov calculation.
Well, I think that's a direct effect of the lifetime of the dark matter.
Yes, but we have to explain it. Yes.
Yes.
Absolutely.
Well, I think
let me ask something to Brian now. Because the Big Bang is sort of the most accepted theory that we have in cosmology so far. And there's also a big part of the community that supports inflation or is working on that. What do you think it would take for, in terms of observations, for the community to, let's say, take CCC more seriously in that respect? Because there's been quite strong opposition in the last year. So what sort of observations could the community make to sort of change their minds in that respect?
Well, it's always hard to get a community to change what they're doing. So it's just a sociological aspect of science. I think there are lingering concerns, raised by the paper that I cited by Joe and Scott, that, were not really synchronously addressed. I would say I did have Roger on to talk about that on the podcast last year, but he had some other important business in Sweden to take care of. So I do think that there are other signatures, like I mentioned, polarization, and it's not as much an issue of sort of criticizing inflation that's needed anymore. I think Roger's been on the forefront of that. There are people that take that very seriously. I think more it would be examining the implications for things like the polarization imprint, like repeating the stacking analysis. Did they get it right? And then I think the statistical kind of nature of it means that we will have to obtain more data. But there are questions, for example, Roger mentioned these very long wavelength electromagnetic modes a few minutes ago. There is this well-known TE anti-correlation at very large scales that's been known since the early 2000s with WMAP data, and even before as a test of super horizon modes in the context of inflation that would have the exact parity or symmetry behavior. So it would be interesting to know, does CCC reproduce that? In other words, I don't feel, Roger and Vahe and others, that you guys are fully exploiting all the information in the CMB. There are some ideas going around, and those are great. And I think I love to hear these ideas. I'm a supporter of new ideas. I'm not, I'm not 100% convinced in inflation's veracity either. But I think there's also a false dichotomy, because people talk about inflation as if it is the Big Bang, the origin of time. Inflation is successful if and only if it is considered as a structure formation theory. So I would like to know, what are the implications for CCC on baryon acoustic oscillations, on the phasing, the synchronicity of these perturbations from the dark ages until today, and then also at the CMB's last scattering surface. But until you mine all the modes that are available, both in frequency, spatial frequency, and in polarization, I think there's still more work left for you to do. It's kind of like when somebody asks you, the contractor tells you, he wants to add a pool to your house. Well, that's fine, if he's paying for it. But to expect the community is going to, all of a sudden take interest in things because they're just, interested in exploring the consequences, I don't think that's realistic. So I would more like, for Roger and Chris and Vahe and others to look at these, all mining the CMB and baryon acoustic, especially for the for structure formation clues, not just Hawking points alone.
No, I think there's an awful lot to do, and I'm happy to agree with you. We are a fairly small community. We need more people to look at these things. Yes.
Great. Yes, so I'm running out of questions, Stuart.
Okay, I'll take it from here.
Sorry, Stuart.
Oh, go ahead. Go ahead.
I just wanted to see if Roger would give us kind of a big picture, convocation or something for where you see the next 90 years and all the things you do, because this is the last session, right, Stuart?
Not just CCC. No, I think there's an awful lot to look at in CCC, which they've just been coming up now. And things you mentioned, for example, which should.
But in consciousness, in quantum mechanics, in wild curvature, all the vast spectrum of things you do, what would you most like to see the next 90 years look like? As kind of a valedictorian, speech to the community and to the world that loves you.
There's a lot in the consciousness aspect too, because I can certainly, listening to the talks yesterday, various things which yeah, I mean, a lot of experiments too, which were, I think it's hard for me to make any judgment here, because should we think of something else besides CCC and consciousness? Black holes, well, they're there, aren't they? Pretty well clear. They're there, and they're being studied very much. So I don't think I should, put my
measurement problem.
Oh, absolutely, the measurement problem. No, you're absolutely right. The measurement problem is absolutely key thing, and that's where also there could well be experiments, and that's just one of the things, of course, Yvette is concerned with, whether you could use Bose-Einstein condensates to test ideas about wave function collapse. Yeah, no, that's a huge topic. The problem there is more, I hate to say we don't have a theory, because when I said that, Philip Stamp jumped on me and said there were all sorts of theories. But I will still maintain we don't have a theory. When I say a theory, I mean a plausible theory which you could actually make predictions and tests and that sort of thing. So I mean a serious theory which would be something you could make pretty clear-cut predictions as a result of the theory.
You have pieces of a theory.
Yes, that's right. It's just pieces of a theory. That's true. And it needs more. It needs more on the theoretical side, as well as on the. I mean, I think there are experiments that could be done which don't directly relate to the collapse theory, but which relate to what was I trying to say here? Well, it does relate to the collapse theory, which, you see, there's a common view. There are these things called CSL theories. And these CSL theories are important. They're modifications of quantum mechanics where you have additional terms which would give you a collapse. But the trouble with these theories is that they all involve sort of a jump in the system, and then you imagine that there's some kind of heating, which is spontaneous heating, and these theories mostly predict that, and that's not seen. I think it's also in contradiction with general relativity, so I would worry about that. So you need a theory which doesn't predict this spontaneous heating, and certain ideas that I have about this would be of that nature, and there would be experiments not simply to test the collapse. Let me not go into this because I think I'd have to go into too much detail. But I think there are experiments there to do with collapse, which aren't directly measuring the collapse, but which you could measure if collapse happens. You see, if you have decoherence, you see, then you lose the purity of your quantum state, and you then go over to a density matrix or something. But that's not really explaining what happens. I think I shouldn't go into this now because it's a little bit aside there.
But do you think we'll understand the measurement problem in the next 90 years?
90 years, yes.
You think we'll do? Okay, very good.
But I'm not going to be around, so you're not going to be able to show I'm wrong, you see. If you're going to say 10 years, you say the next 10 years, touch and go.
Okay,
Yeah,
that's optimistic. That's optimistic.
Yeah, we might see it, yes. Yeah. I did want to make a point about inflation. I didn't comment on that before. But if you do have any substantial inflation and try to marry that with CCC, it's a disaster. Because instead of the crossover being just one nice surface, it stretches it to an enormous thing, and signals will get completely lost. So you could say that any observation confirming CCC is an argument against inflation. And one of the important points about CCC is that it should substitute. I mean, inflation I always thought when I first heard about it, that's not going to last very long. And I was completely wrong, of course. But for a long time, I think it lived and didn't die because it was the only explanation people could think of the scale invariance of the temperature fluctuations in the CMB. You have the scale invariance. But if you have a previous eon, which has its exponential expansion, so it's a bit like inflation, but it's not introduced after the Big Bang, it's before the Big Bang. And you've got to show why that also gives you a scale invariance, which I think if it's the decay of dark matter particles, which is what I claim it is, and if the dark matter particle decay time, the half-life is something like 10 to the 11 years, which is a reasonable guess, then you would see something like the spectral index, which is regarded as the crowning achievement of inflation. But you'll be able to see what it's really telling you is when do the particles start to die out. You see, you've got these dark matter particles, and it's the decay of these particles, which would cause in the next eon the temperature fluctuations. As long as that's exponential, then you will see an exponential effect. But if you start to lose the particles, then you see a deviation from exponential, and that would be the spectral index. So you have to compare the lifetime of the particles with the age of the universe, more or less as we see it now. And it has to be just a bit longer.
But in inflation, the origin of spectral index and the scale-free spectrum is of quantum origin, not of classical origin. So,
well, the decay, I don't know if you call it quantum, because the decay of particles is quantum, I suppose, anyway.
No, quantum in the sense of the field, the delta phi averaged over, it's proportional to T, and that gives you the scale-free spectrum. So the origin would be completely different in CCC.
No, I agree. This is utterly different.
Yes.
But you would see something like a spectral index.
Yes, absolutely, you should, yeah. Mm-hmm.
Well, I think that we should all work, or someone should figure out how to get a compendium of Roger's works, collected works, and send it in a capsule to the next eon. It would save them a lot of time and trouble. So hopefully that'll go forward. Well, let me begin to close this and say, first of all, thanks to Yvette for chairing. Thanks to all the speakers. This is a great session, great questions. Roger, of course, thanks to you for everything. I also want to thank our sponsors, Alvin Clark and Manny Baumick. Thanks to Abby for everything she does. Thanks to Matt George and the crew from Commotion Studios. Thanks to Lowe's Ventana Canyon Resort, University of Arizona College of Social and Behavioral Sciences, and above all, Roger. And Roger, I'm reminded of a birthday card I got a few years ago. I opened it and it said, there is no past, there is no future, there is no present. Actually, there is a present coming to you in the mail, but I couldn't resist the joke because of its physics orientation. So in closing, we're going to try something here. We have a birthday video without sound, and I'm going to ask those of you who can or are willing to unmute, and we're going to try to sing happy birthday to Roger. And I'm told by the Commotion Studios guys that this might break the internet. So if it does, the session, the conference is over, and we'll just go on from there. And hope to see you back for the next consciousness conference or some other event. And Roger, Brian said it. We love you. We need you. Stay healthy. Keep coming back, and we'll see you next time. So I'm going to get out of the way so you can see the video here. Oh yeah, I don't have to. And those of you who are willing, please unmute. And who's going to start? Yvette, why don't you start? I think you probably have a good voice.
I can warn you, it's going to be a disaster. Because my son Max spent a lot of time with choirs and getting them to sound as though they were together. And that's a big operation.
Well, we'll just do the best we can. So, is everybody ready?
Yeah.
Ready.
Happy birthday
birthday
to you. Happy birthday to you. Happy birthday, dear Roger. Happy birthday to you.
Happy birthday
To you.
Yay.
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 Thank you very
All
much.
right. Thanks, everybody. Bye-bye. See you next time. Stay well. It was a great week.
Thank you.
Appreciate
Thank you
it.
very much.
Thank
Thank
you
you,
so much
Stuart.
for organizing
Thank you,
this
Stuart.
wonderful event.
Fantastic
I'm very
experience.
happy
Thank
to
you
do
very
it.
much.
Thank you. Bye-bye.
Yeah, it's been
Bye-bye,
fantastic
everybody.
Organizing this.
The Royal Swedish Academy of Sciences has today decided to award the 2020 Nobel Prize in Physics with 1/2 to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity.